Good morning, everybody. My name's Alan Werity, and on behalf of the Royal Society of Edinburgh, I'd like to welcome you very warmly to this one-day meeting on flooding. I'd particularly like to thank our speakers for today, many of whom have travelled at quite a distance to be with us. And I'd also like to thank our sponsors who have underwritten some of the costs of this meeting, SEPA, Scottish Natural Heritage, the Scottish Government, and the James Hutton Institute. I've been asked to do a little bit of housekeeping, so if you'll just bear with me for a moment. No fire warnings are anticipated, no trials for fire warnings are anticipated today, so if there is a fire warning, can you please follow the instructions on the screen? There are two exits, the side door here, the door at the rear of the building. Follow the route indicated and assemble across George Street, just outside the George Hotel. Can I also ask you to switch off your mobile phones if you haven't already done so? And can I advise you that the conference is being recorded, so if you wish to reprise any of the contributions in terms of the oral record, you'll be able to do that by downloading from the RSC website. We also have a professional reporter with us today who will produce a written report of the meeting, and that report will be with you a few weeks after the meeting to provide you subsequently with a written record. Let me just give you a thumbnail sketch of the Royal Society of Edinburgh, which you may not be familiar with. The Royal Society of Edinburgh is Scotland's national academy. Goes back to 1783 when it was founded by some of the luminaries of the Scottish Enlightenment, David Hume, James Black, Adam Smith, and James Hutton. And its purpose is for the advancement of knowledge and learning, for the betterment of the social, cultural, and economic well-being of Scotland. And it's been doing that for nearly 250 years. Of course, it's changed over time. We now have nearly 1,500 fellows, and a lot of the work of the RSC is engaging with the public. And I would regard this meeting as a very good example of that. A group of fellows felt that the issue of flooding had once again risen quite high in terms of public awareness, and it was triggered by the events of the winter of 2014 and 15, and that was the initial gestation for this meeting. A meeting which is really in two parts. The first part this morning, this afternoon, will comprise a whole series of technical presentations from some of the leading experts in this field in the UK, supported by a whole series of posters upstairs, and I do urge you during the lunchtime break and the tea break to go and look at the posters and engage with the poster presenters. And then, by way of an important addition to that technical meeting covering the morning, the afternoon, we're hosting a public debate this evening. So there will be a half-hour pause between the end of this meeting and the beginning of a public debate, which will start at 5 o'clock and will run to 7, maybe 7:30, depending on how many questions the panel has to field. I do urge those of you who are minded to stay the course to linger for that public debate, because what we want to do in that debate is to take some of the issues which we'll have discussed during the morning and the afternoon and invite a wider dissemination and discussion with the public in that evening session. So let me now try and provide a little bit of background and context to the meeting as a whole. It was, as I've just indicated, triggered by the floods of 2015-16. If you cast your mind back to that period, it was quite a remarkable period. We had about 14 weeks of persistent, really incredibly severe weather with storm after storm coming in across the Atlantic. And the magnitude and the frequency of those storms was such that the impact on domestic properties, commercial properties, agriculture, the transport sector was very, very severe. And if we rank it in terms of severity, I think we can rank it in UK terms, certainly alongside the 1947 flood. Its impact, I think, across the whole of the UK, and most notably in parts of Scotland, was really quite remarkable. this, in a snapshot, is what was going on. We had this constant series of storms coming in, driven off the Atlantic by persistent southwesterly airflow, linked with an unusual, as it were, trajectory of the jet stream, but also associated with a very high value for the North Atlantic Oscillation, a very positive phase, and also a strong El Nino signal in the Pacific. So if you like, a whole series of circumstances came together to produce that very unusual 14-week period. And it resulted in a series of storms. The Met Office has very helpfully begun to give them names. It's much easier to recall a storm if it's got a memorable name. The two which, of course, were particularly severe and had a particular impact in Scotland were Desmond and Frank. And if we look at those two, here is a very brief account of the rainfall record. I'm sure most of you know that in the Lake District we experienced the most extreme 24-hour fall ever recorded, 341.4 millimetres at Honeston Pass and 405 millimetres in Thirlmere in 48 hours. So new UK records were registered in the Lake District. And if you look to the map, that is a map of the monthly rainfall, and you can see large parts of Scotland had monthly rainfall figures in December in excess of 250% of the normal. If we now turn to runoff, just one record, the Dee at Wood End. Now, the Dee is one of the most well-documented flow records in Scotland. It goes back to 1929, and that value of 1,362 cumex was the highest flow on record. But there were also very high flows in the borders. Records were broken on the Tyne, the Tweed, and the Nith. And if you look again on the right-hand side, you can see these are the again the monthly values of flows for December 2015 and January 2016. Black indicates exceptionally high, and when they're circled, as you can perhaps see, that represents a new record. So we are looking at quite a remarkable hydrometeorological event during December and January of that winter. By the way, can I thank CH who have provided a most valuable summary of all those events, and if you're not familiar with it, go to the CH website. You can download it and find all these figures and much more besides. The impact, well, the impact in Scotland was widespread. Let me just focus on Aberdeenshire because that was the local authority most severely impacted. You can see the figures, I think they speak for themselves. Damage to homes and businesses. The caravan park was spectacularly destroyed, as you can see in the picture there, but also very extensive damage to the infrastructure, bridges, even roads. The A93 was partially washed away. They're very rapidly repaired, and the repair cost for Aberdeenshire Council was in excess of 5 million. Now, of course, one of the issues which came up at that time, which is hotly contested, and I'm sure we'll be addressing in our presentations this morning, what is the link of those events with climate change? Well, I'd like to just read to you two statements by Julia Slingo, recently retired as the Met Office Chief Scientist, because I think these bear the imprint of being truly authoritatively expressed and also very precise. There's an increasing body of evidence that the UK may be experiencing extremes of rainfall that potentially lie outside the bounds of what might be considered normal in terms of frequency intensity. And then the telling final sentence, this is in line with what might be expected from climate change. So that climate change signal, I think the Met Office, which has to be rather cautious and conservative in its statements, is now beginning to say that link is getting stronger and stronger. That's looking back to that winter. Let's now, as it were, look at the present, because I think there's a very appropriate policy context, which is another reason for timing this meeting at this juncture. We've had the Flood Risk Management Scotland Act in place since 2009. Last summer, the flood risk management strategies and plans were published and are beginning to be unwrapped. So we've come to the end of, as it were, the first cycle of delivering the Flood Risk Management Scotland Act. We're moving into the next cycle. We've got the Flood Warning Service, which is under review. We've got the implementation of new flood insurance procedures through Flood Re. We've got a new climate change risk assessment coming up quite soon, and the work on flooding has already been done for that, and it continues to demonstrate the very severe impact of flooding as one of the consequences of climate change. So with that all in mind, we have convened this conference, and we've asked each of the speakers to address one of each of these questions in turn. What we're trying to do is to look back and, as it were, reflect on the lessons which we might learn from those winter floods of 2015 and 16. But then I think we want to look forward quite positively in terms of the next cycle of delivering the Flood Risk Management Scotland Act. How can we do better in ensuring that our most vulnerable communities are protected to the best of our ability? So with no more ado from me, I would like to invite David Feckney to come up and take the chair and to introduce our first two speakers.
Thanks, Alan. Good morning, everyone. My name is David Feckney. I'm a Senior Manager in SEPA's Flood Unit, currently managing the Flood Risk Team. And put simply, that's the team that provides the evidence base for flood risk management, including Scotland's flood maps and the information and advice to support the flood risk management planning and land use planning process. I've been a hydrologist for over 30 years, with just over half my career in flood risk management, and I've been very closely involved in the shift to the risk-based, plan-led approach to flood risk management that we now follow here in Scotland. In recent years, I've been focusing on ensuring that my organisation, the Scottish Environment Protection Agency, has been able to evolve to take on the responsibilities conferred on us by the Flood Risk Management Scotland Act. And as we enter the second cycle of flood risk management planning under this legislation, I'm very pleased to say that SEPA now describes itself as doing two things. We do regulation and we do flooding, with one of our 4 corporate outcomes being that the impact of flooding is reducing. I was delighted today to be asked by the RSE to chair this first session on climate change and changes in future flood risk. These are not only of great interest to me and my organisation, but to all that are involved in managing flood risk. In my view, these are the big challenges to overcome, and as we aim to reduce the impact of floods here in Scotland. This session will last until about 11:40. We have 2 speakers, each with about 25 minutes each. I'll just check that with them. And then we have a 10-minute short question and answer session. Our first speaker of the day is Chris Kilsby, Professor of Hydrology and Climate Change at the University of Newcastle. Chris is Director of Research in the School of Civil Engineering and Geosciences. Chris develops and works with statistical and physically based models of rainfall, catchments, cities and water resource systems. Applications include flood risk management, climate change impacts and adaptation. So if you'll join me in welcoming Chris to the podium, thank you.
Thank you very much, David, and thank you to the Society for inviting me to speak and, in fact, entrusting me with leading off what looks to be a very interesting day. So I'm going to be giving you a statistics lecture. I hope it doesn't come across as an undergraduate lesson. Quite a few details here that I'm probably not going to have time to go into entirely, so I can make the presentation available to anyone who's interested and ask me afterwards. So I'll be referring to, in particular, to a couple of papers I've put together with a colleague of mine, Francesco Serinaldi, who together with me addresses these sort of questions with the university and also with some support from the Willis Research Network. So, expanding on the question which Alan posed, the motivation for this strand of work, I've tried to encapsulate with a few of these questions. We've had some of these apparently record-breaking floods, certainly severe floods, Are they related to climate change? Are they in fact record-breaking? And I'm going to try and review some of these fundamental questions in the next 20 minutes or so. So what do we mean by record-breaking? Is the flood regime changing? If it is changing, what do we mean by changing? There's a string of difficult words I'm going to use in the next 20 minutes. One of them is change, one of them is trend, and I'm going to come on to some longer ones like stationarity to look at. So if we can't say there's a change now, and a sneak preview, I'm probably going to say that from a statistical standpoint, will we be able to at some point in the future, and if so, when will that be? So these are some of the background questions to bear in mind. So I'm going to split the talk into a few sections so we can see where we're going. Bit of a fundamental look at changes, trends, and stationarity to begin with. So we've got some terminology in common. Then I'm going to have a very quick look at record breaking from a statistical point of view, and then look at attributing these extreme flood events to climate change, again from a statistical point of view. So I'm going to be looking pretty well entirely at the data here, the extreme floods, peak flows, extreme rainfall, associated with the extreme events themselves, and I'm not going to be looking at the meteorology, the physics behind it at this stage. I'll come back to that at the end. So let's think of this as looking at the numbers that have been happening that we've had in the last whatever years. So this sort of business, we start off typically with a time series of flood peaks. So this is a typical record from the UK, about 50 or 60 years worth. It's actually a peak over threshold time series for the South Tyne at Hayden Bridge, close to home for me at least. And first thing you might notice is there's some variability here, and in fact many records have remarkable variability without apparent outliers thrown in at various points. And because of that, the typical approach to analysing or classifying this sort of data is a statistical one. And a lot of work's been done considering such a series as a stochastic process, i.e. a random process. And if we're going to do that, the rules are it's got to be what we call IID, independent, identically distributed, shorthand. What does that mean? It basically means these are numbers. We consider these annual or POT records to be drawn from a hat, rolling the dice each year or whatever, with no reference to the previous record. There is no time dependence from one event to the next. The memory's wiped clean and we move on. And crucially, this is a single distribution that we're drawing from. So there are no changes in this. It's a stationary process. And those seem to be fairly strong assumptions. And I think a lot of hydrologists would disagree and say, well, I think things are clearly changing. But bear with me. This type of process can sustain really quite enormous variability. And some of the variable processes we see here, popular analyses include things like clustering. It appears that we get clusters of floods, and this type of regime of flood-rich and flood-poor periods is pretty widely talked about, if not understood, and I think it's actually Alan Werrity and co-workers who first introduced this sort of terminology some 20, 30 years ago or more. Other very popular analyses now include looking for trends and looking for changes, either monotonic linear trends or some abrupt change in regime. So remember this 50 or 60 year period, perhaps having in mind that it looks like there's some sort of increase. We've had some of the biggest events on record in the last few years. The highest peak flow recorded at this station was 2005. The 2015 Desmond didn't quite make it above that, although in other parts of the Tyne Basin it did exceed the 2005 levels. Okay, I mentioned trend analysis, so there's some recent literature looking at trends here. One of the methods being tried out is to fit time-dependent models to these observed records. So one of these was published 2 or 3 years ago. Prostacimi, Shelson et al. At the time at CEH, and they fitted a log normal distribution to these random stochastic numbers, but with a time-varying coefficient increasing over the period. A lot of data, but typically and crucially only about a 50-year period. And they found some significant trends using standard statistical methodology, the Mann-Kendall tests and so on. And they're plotted up on this diagram taken from that paper. And you can see some increasing trends, some decreasing trends in various parts of the country with some sign of spatial coherence. It look like there are regions responding together. The crucial point I'm trying to draw from this paper, though, is they found that they were trying to answer the question of, has there been a significant change which threatens flood protection standards and safety margins? And they found that there's actually insufficient data to overcome the uncertainty in these estimates using this time-dependent approach. Okay, so if you can't prove this with that sort of period, should we be fitting time-dependent models? Let's look at this in a bit more detail. Very influential paper was published in 2008, which has caused a bit of a stir in statistical hydrology and various other circles. It's been cited some unbelievable number of times, probably because it had this very provocative title of "Stationarity is Dead." And they claim that climate change is now demonstrably undermining this basic assumption that we can look at the past records to facilitate management in the future. Now, okay, it's clear that there are some changed regimes where the past is no longer a guide to the future. But when it comes to extremes, based on the evidence, I would maintain, and a lot of other researchers have put this very strongly, including those referred to here in USGS and various other places, that you cannot reject this concept of stationarity. We can't prove with the extreme events themselves that we don't have a single stochastic stationary process still operating. I'll go into that in a bit more detail. These hydrologic series of extremes, and I should stress these aren't monthly flows in a sequence which do exhibit dependence one month to the next. These are seemingly random events which aren't connected. Typically, we might analyze those as a combination of fluctuations about a trend that we've got, some seasonality, but crucially there is this large irregular random movement, as Metalis referred to it in an important paper in 2012. If we impose some non-stationary component within this, we have to know where that information is coming from. We can't derive it necessarily from the data themselves. And I'll try and show the uncertainty arising from imposing and assuming this deterministic component. So here's it's actually a US time series, which has been widely used in some of this research. And this is reported in a paper that Francesca and I wrote 2 or 3 years ago. So this is the Little Sugar Creek. It's an urbanized catchment, and these are the raw data. And it looks like there might be some sort of change here and some sort of rising trend. So various people have fitted various trend models to this. This is the stationary case that you just do a best fit line through the middle. This one allows for a discontinuity followed by a rising trend, and this is some best fit non-linear process. What we show in the paper called Stationarity is Undead is that these 3 models are equally well fitted. Statistically, you can't say one of those is better than the other. And crucially, if you plot confidence intervals on extrapolations, in the stationary case, of course, the confidence intervals stay constant. We don't get extra uncertainty in the future because nothing's changing. But if we have particularly this increasing trend, the confidence intervals get wider and wider, so we can't actually make useful predictions out into the future. Okay. Next, quick check of words, trends. What do we mean by a trend? This is another paper we're putting together. It's been submitted for publication in Water Resources Research. This considers these 2 synthetic generated time series of peak flow data. Sorry, these are the annual average discharges in this case. It looks like there might be some sort of trend. But actually, the history of these series, we generated them, in this case, using a non-stationary case with 2 regimes. So it shifted at this point. But the second one is just chosen, perhaps quite carefully, from a stationary series. And this shows the sort of variability you can get within, in this case, a 2,000-year-long series of flows, but they're stationary. It's one distribution used to generate all of them. So you can end up with 2 series which look very similar. So actually, just from the data, you don't know, you can't say which of these cases has generated that time series. So just from the data, I would stress that statistically you can't infer these non-stationary trends. Okay, so to make trend analysis even more difficult, perhaps even futile from the extremes themselves, let's have another look at that South Tyne record. This is the POT series 1959. So claims of record breaking within that, okay, it's breaking the record within that period, but actually the full data set might look something like this. So I've put these extra 8 or 9 historic records in from work that David Archer put together over many years. And all 8 or 9 of these are thought to be close to or larger than the 2005 record. So if we're doing record-breaking analyses, what period do we use? So that 2005 record-breaking flood doesn't look like much of a record compared to, for example, 1771, which wiped out all the bridges on the River Tyne from top to bottom, bar 1. So the period we're using here is really very difficult to establish, and we have to have some good reason, some philosophy for deciding what period we're actually going to use for our record-breaking analyses. Okay. In the interest of time, I think I'll keep moving. A bit more on record-breaking. What do we actually mean by record-breaking it's rather in doubt depending on what period we're using, but whatever period we use, if we're assuming some stochastic process here, we have to expect records to be broken. Just because we had a big flood some years ago doesn't mean we're not going to get a bigger one. And in fact, if we assume events are IID and these stationary stochastic processes, then we get this sort of behavior. So let's take observations every year of annual maximum flows, these green chaps, and let's say we've started breaking records. So the first observation is a record breaker. It's the biggest. And then let's imagine we get these breaking records at various intervals. If we call the period from the beginning of the observations through to the most recent, the rth broken record, if we call that M, if we've got a series n long, so we're here now, what can we say about when we expect the next record to be broken, the r+1th record? So if we say the record is n long, the time from the beginning of the observed period to the last record broken is m, and we imagine we've got an economic design life, a planning period ahead of h, then we can do a very quick calculation. It's just, we can show the probability of the record being broken in that period h is just given by this very simple expression, n plus h minus m over n plus h, and that just assumes an equal chance of the record being broken every year. So what does that mean in real numbers? Let's imagine a typical case. We've got a 50-year-long record. The most recent broken record was 30 years ago, so m is 20. Let's say there's a design life of 50 years, then the probability of breaking the record, and I haven't talked about distributions or magnitudes here at all, just for any stochastic process, the probability is 80%, okay? So it's no surprise when we break these records. What might be surprising is the margin of breaking these records. So in this case, some people have looked at the ratio of the size of the record to the previous one. So, and call that a surprise index. It's quite good fun for statistics, isn't it? So they worked out this index of surprise, the margin of breaking the record, the latest one y and the previous one x of n, divided by the ratio, the margin of breaking the previous one, x of n minus x minus 1. And you can do some statistics with this. Some other work that was done at CH looked at this surprise index, and no surprise to me, perhaps, 14% of stations around the country report a surprise, so they do happen. So we shouldn't be surprised. Okay, thank you. And the other interesting thing here is that there's a spatial coherency where these surprises happen. So actually, quite a few of these, they managed to relate to big events that were a surprise to the authorities at least. So there's some rationale here, but the main thing is we have to expect records to be broken and we have to expect surprises. Okay, a very brief look then to finish off with the question Alan put to me. I haven't ignored it altogether, I promise. So these extreme events and broken records are happening. Can we relate them to climate change? Okay, so there's a lot of work being done on, it used to be on detection of climate change, and actually we have detected climate change in various measurements now. Can we attribute these to climate change? From the data themselves, from the extreme events series, I'll show you that I don't think we can at the moment. For some variables like global mean surface temperature, it's clear that we can attribute that to climate change. So these are series with strong coherence spatially and in time, and we can realistically look at trends with these. That trend word that I think of as a bit of a dirty word in terms of extremes, it's fine to use it for things like global mean temperature. And we can attribute this. I mean, for the last 10 or 15 years, publications have shown by model studies that, and some reasonably sophisticated statistics with a thing called optimal fingerprinting, that the signals, the fingerprints of climate change are all over global mean surface temperature. Okay, how do we do that with individual events, though? So, we've all heard, or perhaps some of us have even asked this question, was this recent flood caused by climate change? And this is the central question. The usual way of dealing with this now is to say, well, you don't just ask about the event so directly, but you can say what fraction of the probability of this event happening is attributable to climate change. And there's a methodology has been developed over many years. It actually first came out with taking on the tobacco industry for incidence of lung cancer. This is the fraction of attributable risk, and it's very simply given by this expression. The fraction is 1 minus the probability of the event happening before climate change, divided by the probability of happening in the future climate. This is fine. I like this. This is all good stuff. But the point is that this is related to the frequencies of occurrence of these events before and after climate change. And when you've had a big event, you don't actually know what the return period or the frequency of occurrence of that single event is. And typically, well, one reason you don't know is you've only got often a 50-year record to work with it. So it's quite reasonable to ask, has this frequency changed or will it change in the future? But I don't believe we can safely relate that back to the single event. So quite a few studies have been done on this now, which use models to simulate what's happened over thousands of years before climate change and thousands of years after. One of the first ones was this one, Paul et al. 2011. There was another one in 2015 that was submitted but rejected from a journal, Hess. And this does the typical thing with the extreme value plot of rainfall, extreme rainfall in this case, in blue before climate change and then after in red. And there's clearly a difference, but what we don't know is where the particular event lies on this. We can estimate it, but the uncertainty is uncomfortably large. So similar things been published recently on some big floods in Louisiana, and they've even shown the increased return period, the decreased return period or the increased intensity for a given return period using the same methodology. So, to conclude, first of all, on the fundamental question of change and trend detection using the flood data themselves, I maintain that it's still crippled by uncertainty because we've got small samples. In the methodological sense, we don't have enough data to reject this idea of stationary processes. And in fact, for a trend to be present, there has to be a deterministic component. And a number of papers and thinkers have now put forward that you can't find a trend and then think of the mechanism for it. You have to do it the other way around. So for attribution to be done successfully and credibly, you have to come up with a hypothesis, probably using models, for a trend or a change or a step change or whatever it is, and then show that it happens in reality. So you've got to do it that way around rather than the Nostradamus type of business where, something's happened. Let's go back through all of Nostradamus's predictions hundreds of years ago, and bingo, he predicted that Hitler would happen. And probably Trump, for that matter. So there are some significant issues with this sort of trend analysis using the data alone. And the same applies with attribution using the data alone. However, this just goes to show that you can't, despite some people's claims, you can't show anything you like using statistics. In this business, statistics on their own are not enough. We just don't have long enough records of these extreme series. So we have to bring in and integrate information on the causes of these extreme events. Certainly the rainfall, the background climate, the hydrology of the whole business, and how we incorporate that is the interesting research challenge. And clearly we can use other observations of rainfall, and we can use other observations in space and time. And we can also rely more and more on climate models, hopefully as they become more detailed. And I think you'll hear a bit more about this in the next talk from Nick Reynard. I give a whole load of the references here if anybody's interested, but I'll stop there. Thank you very much.
Thank you very much, Chris. That was a very interesting presentation. Great start to the day, I think, and lots of food for thought there. Our next speaker is Dr. Nick Reynard. Nick is Science Area Leader for Natural Hazards at the Centre for Ecology and Hydrology in Wallingford, and is presenting to us this morning on changes in future flood risk. Nick's work includes research into flood and drought prediction and forecasting, particularly the investigation of the implications of environmental factors, including climate change, and the development of techniques for detecting and attributing trends in environmental data sets. Nick.
Thank you. Thank you very much, David. Thank you very much to the RSE and to the organisers and sponsors for inviting me to come and talk to you this morning. It's a great opportunity, and I hope you'll find something interesting in what I'm going to say. I will pick up on a couple of things that Chris talked about, but I'll start by talking a little bit about the natural hazards research and the floods research that we do at CEH, just to give a flavour of the breadth of work that we undertake. I'll spend a few minutes, maybe 5 minutes, talking about some recent events and going over and adding a little bit, perhaps, from our point of view to what Chris was just saying. But I'll spend the bulk of the presentation on some of the work that we've done at CEH in terms of providing evidence for the adaptation debate, or the adaptation decisions. How do you make decisions about climate change and incorporate climate change into decisions about flood management? And I'll talk about some of the science that we did in support of DEFRA and the environment agencies across the UK. So natural hazards in CEH is pretty broad. The reason for putting that up at the top really is just to talk about what we do is we do some of the fundamental science about understanding the threats from natural hazards. And we do a lot of work trying to then develop models and progress our understanding in terms of predicting and forecasting what these hazards may look like in the short and long-term future, in support of the management and mitigation of those hazards. So we like to do our research with impact. So we like to have the story that we tell in terms of how the research is picked up and used by decision makers, by regulators, etc., etc. So it's broad in terms of its science remit in CEH. It covers droughts, it covers floods, it covers some aspects of non-native invasive species, impacts of volcanoes, etc., etc. But the bulk of it is really around flooding. I split our flood research portfolio into 3 broad areas. Really to do with the time period we're thinking about. So the first one is flood estimation. So what are we dealing with right now, here today? What do we understand as our current flood risk? And the methods around that are encapsulated in the Flood Estimation Handbook, which has been going or evolving since the mid-1970s, and present the data and some of the methods to allow people to understand what their current flood risk might be anywhere on the river network in the UK. And last year we launched that as a web service so that the data are now available in a more modern format than buying a CD-ROM and trying to get the data out of those. So we do some flood estimation. What's our current flood risk? We do a lot of work in terms of providing modelling support for flood forecasting. So CEH models are at the heart of flood forecasting services in England and Wales and the one in Scotland as well. And they provide a national scale forecast in terms of river flows for the next few days. We also use those sorts of models now to provide things like a hydrological outlook. So what might the outlook be over the next few months? This obviously is perhaps tuned a little bit more to the low side, to the drought side, than it is to the high side. But there is information in some of those models driven by some of these seasonal forecasts in terms of what might happen over the next 1 to 3 months. And some recent work that we've been doing under the umbrella of the Natural Hazards Partnership is to develop a surface water flooding hazard and impact tool. So this is quite new work that we've taken on in recognition that some of the recent events that we've seen have been, as they always are, a mixture of flooding sources. So they're not just fluvial, they're often pluvial, surface water flooding, non-river flooding is mixed in there with it, as is groundwater flooding. So they're always a mixture, and it really exposed, I think, us to our vulnerabilities to things like surface water flooding in some of these recent events. And we've been developing a surface water flooding tool that blends the hazard of flooding with the impact by working with some colleagues in the Natural Hazard Partnerships from the Health and Safety Executive. But today, I'm going to talk mainly about the last one, which is thinking about long-term prediction. So how do we use the science that we do to support what people might do about climate change if you've got a flood decision to make? So we've been doing decision making, thinking about policy development and supporting policy at DEFRA and long-term adaptation planning. So we've heard a lot. I think the press have come up with this title for this slide is "Are Floods the New Normal?" I think there's a lot you can argue about that. It doesn't actually mean anything, as Chris probably just said in his slide. But there have been a lot of floods recently, and we know this. It is apparently something that is the new normal. Are they the new normal? Well, that's the list of events. I mean, it's not the complete list of events. It's the list of a range of events. There's some there that are quite small-scale, local, like Boscastle, but there's some that are very large, almost national-scale events over the last 15 or so years, perhaps going back to starting in Easter 1988. So, you know, Chris mentioned flood-rich and flood-poor periods. I think we can definitely say we're in a flood-rich period if they're not the new normal. That's true. It's quite a long period. So is it the new normal? I mean, these are all fair questions, but as Chris said, they're very difficult to answer. So if you look back, actually, were floods the old normal? If you go back to the decade of the mid-40s to the mid-50s, there are an awful lot of flood events then as well. Perhaps slightly different in some of the driving mechanisms. For example, the 47 flood was a snowmelt-driven flood. But even so, there was a very flood-rich period back in the middle of the last century. So the idea of using the recent past to say this is the new normal is difficult to say the least. I'll go over the next slides fairly quickly because some of them just sort of reiterate some of the messages that Chris was giving out. So if they're not becoming more frequent, are they becoming more severe? Is there a trend? So this is the Thames, the longest record that we have, going back to 1880, and there's a picture that, like Chris showed, with a trend through the middle of it that is absolutely stationary, is absolutely flat. There is no trend, and you can see on the marks here that we've got that some of the recent events actually, in terms of the levels, don't really compare to some of the earlier events in the 1800s. So looking at the data, it doesn't seem to be that they're getting more severe. This, again, is about record length. This isn't about different types of trend. This is just about fitting the long-term trend. So there you can see the nice long Thames record with a flat, no trend through the middle of it. Then we've got the Severn, which goes back to 1920s. And again, the overall trend is flat, but there's a tantalizing increase in the running mean, the black line at the end, pointing to an increase, which overall, of course, gets absorbed into the natural variability and the longer record, and so overall there's no trend. But then when you come down to, say, the Tay, which is much shorter, starting in the 1950s, you're basing a trend analysis on that, then that tantalizing trend becomes the trend in the series. So this is about, as Chris said, if you're basing a trend analysis on 50 or so years, then you can easily pick up the wrong sort of signal from that, from those data. This is some work that was done a few years ago now by some colleagues of mine, Jamie Hannaford and others at CEH, looking at trends in high flows. And these are two different types of maximum. There's the annual maximum here. So this is the annual maximum flow in any year, the time series of that on your right. And on the left, we have the 30-day maxima. So this is the 30-day flow, the highest flow over a 30-day period in a year. They look very blue, and the size of the dot also tells you about the significance, but actually there is no significance in the one on the right. There's no statistical significance in the one on the right. There are no trends in terms of the annual maxima, as Chris said. The data just aren't there to support that sort of analysis. And even though they look fairly similar, there is a little bit of significance in the one on the left, suggesting that we are seeing perhaps more periods of higher, more sustained high flows across the country. But even so, these signals are fairly weak, and it's difficult to draw any conclusions. So, if it's not about trend, is it about variability? Is it about volatility? So if you go back to 2012, we've talked a little bit about 15-16 events, the 13-14 flooding, but if you look at 2012, it presented a very particular year to us, which was incredibly variable. We entered the year, it was coming to the end, as we know now, of a 2-year drought. So in March 2012, we were very concerned about water resources and the water resource position going forward through that year. There were obviously lots of things happening during 2012 that we didn't want to run out of water for. And so there were plans being put in place for significant drought through the summer. And as you can see there on this England and Wales, apologies, England and Wales National Runoff Series, there was a record minima recorded at the end of March. It then started raining, and it rained an awful lot in April. And I think as a monthly total rainfall for the whole country, the return period was around about 300 years, as an estimate. And it meant that by the end of April, just within a month of the lowest minima, we then recorded a new maxima on the series. And that went on. Obviously, there's some variability in May, but then we had the very wet summer, and it went on and on. So this was a roller coaster, hydrological roller coaster, that we went through in 2012. So is this climate change? Is this the trend that we're looking at? Is it more extreme events, more low flows to more high flows in more rapid succession? That's another question that we could ask. So, again, I won't say much about this. Chris gave a nice introduction about what this sort of work is. This is about thinking about individual events, about using the weather at home data from Oxford. So this is the thousands and thousands of runs that the Oxford do that have anthropogenic effects of climate change included, and thousands that don't have that effect included. And then from those two time series, we select certain events and look at whether or not that event was more or less likely to have occurred because of anthropogenic influences or not. We can have the debate as to whether this is attribution in its formal sense or not, over coffee maybe, but this is about looking at the fraction of attributable risk for those individual events. Chris mentioned the rainfall that Paul et al. Published back in 2011. This is the hydrological work that came from that Alison Kay from CEH published in 2011 as well, following that paper, which looked at the hydrology and just showed that for 8 catchments driven by all those time series, in 7 of the 8 catchments, there was a clear signal that that type of event, autumn 2000 event, was more likely to have happened because of climate change than not. So that was what we did on 2000. We've since just published a paper on winter 2013-14 as a season. And again, the signals are a little bit harder to pick out from this. If you look at the diagram there on your right, the red cloud is the cloud produced from the anthropogenic influence, and the blue is from the non-industrial runs of the model. And you can see there is an increase in the attributable risk. But it's a little bit more complicated conclusions from these papers. The other thing that this paper did, this was focused on the Thames. So what we actually did was we worked with Jeremy Benn in terms of taking the flows and driving them through their models to work out actually what about, instead of going from just rainfall to river flow, what about damages? What about the costs of this event or this season? And again, we were trying to attribute climate change to these changes in the costs driving that, and working with them now to break that down spatially, to go within catchment, because that was just looking at Thames at Teddington. We're now going to be looking at areas within the Thames catchment doing this sort of work. So that's all I wanted to say about the bit around the past and the current, if you like. So what about the future? What does the future look like in terms of flooding, and how do we assist people who are trying to make decisions and think about what to do about climate change? There's a very logical argument here that we should see an increase in flood frequency or flood magnitude under climate change. The first is basic physics. The world is getting warmer. We know that. Chris talked about that in his presentation. And basic physics, Clausius-Clapeyron, suggests that if you have a warmer air column, you hold more water. So when it rains, you'd expect to get more rain, either more intense or more of it. That's basic physics. So you might expect that just from a warmer world, you would get more rainfall, you might get more flooding. We have in the UK seen, across the UK, an increase in winter rainfall over the past number of years. There is some evidence also for increased rainfall intensity, so that supports, those both support the first bullet. As I've said, we've seen a cluster of recent flood episodes. That's evident in the record. There is some consistency between what we've seen and climate change scenarios. The quote from Julius Lingo that Alan mentioned earlier on went a step further than I think we've been before. I think I'll remain a little less. Well, I'll stay on this side anyway. There is some consistency that we see in these events. But as I've said, we have to think about natural variability. Where we sit on the globe is an incredibly variable, right on the polar front, right next to a massive ocean, very variable climate. Therefore, we have massive natural variability, and we arguably do not understand our natural variability at the moment. So trying to then unpick climate change signals from that and then predict future that is beyond our current natural variability is incredibly difficult. So how might you do it? So one way you could do it is to run a national model. So this is based on the CEH grid-to-grid model, which is a national model, 1 kilometre resolution, run for the whole of the country at the same time. And you can look at the river network anywhere in the country, and you can use outputs such as a regional climate model from the Met Office to drive that and look at what the changes might be across the whole country. This is very nice if you're wanting a strategic overview. If you want to look at the country and you want to see those areas look like it might increase, those areas look like flood peaks might decrease. So there's different return periods here. So if you say look at the 50-year return period there, you can see decreases down in the south and increases further north. That sort of strategic sort of overview. The problem with this is how do you use this for any sort of decision making, because that's just one realization of the future. That's one scenario from the RCM. You might have 2. You might have 11, as we had at the last lot. But you can't keep running these models to sample the uncertainty around this and actually come up with any sort of support for people who are trying to make flood management decisions, for example. But you can take a national overview and do it that way. You could look at an individual catchment and do the full-blown uncertainty type analysis around that. So for this, you can run your catchment model, and you can run it thousands and thousands of times, and you can run all sorts of scenarios through it to try and understand, what the changes might be. So for this particular one at Tenbury, you can see that the changes are all above 0. But the range in the changes, well, nearly all of them, the change in the changes are huge. They go from just slightly below 0 up to nearly 80% increases in flows. And that's using all of the data that you can throw at the model. So again, how does this help in terms of making decisions? What would somebody who is in that catchment trying to think about flood management over the next 50 years actually do? What would you build? What would you do? What would you plant? So that's really difficult. And it's interesting. Scientifically, it's very interesting, and we love doing this sort of thing, being geeky scientists. But actually, how does it actually help anybody? So 5 minutes. Right, I'll rush through this bit. So we were asked a few years back to think about this. The current guidance for flood management was 20%. Add 20% to river flows and you'll be okay for climate change. Precautionary even. You'll be absolutely covered. That was the guidance. We were asked to reconsider this, please. Is it precautionary given new science? And can we come up with regional guidelines? So we undertook a modelling exercise, as we do, with 150 catchments to look at the climate sensitivity of catchments to changes in climate, to see what we could find out. What we decided was to reverse the problem. we're always being asked, what does this scenario mean for this hydrology? So we decided, well, let's think about the hydrology first. How does the hydrology react to changes in climate? Not a specific scenario, but generally to changes in climate. And we developed this sensitivity-based approach, which didn't depend on scenarios until the end. And so what we did was we forced each catchment through a whole number of scenarios, but they were structured by a whole range of changes. So it could be an average of 10% increase in rainfall in every month, or it could be that rainfall in the winter changed much more and it went down in the summer, which is what these harmonics on the left over there are showing. And all of those scenarios were run through our model, and the changes were put on this sensitivity diagram here on the right, which just basically shows that as you change, the average changes on the y-axis over there on the left, and you change the amplitude of the changes, you get this grid of changes. And that pattern tells you how that catchment reacts to changes in climate. There's lots more changes in climate we could put in there, but we haven't. But that's how it changes to these sorts of, that's how that reacts to these sorts of changes. Not scenario dependent. We did it for all these catchments, and you get a nice bit of wallpaper there on the right that shows each one for each return period. But you can see, we can't really see from that, but actually the patterns change, and the patterns change according to the type of catchment that you're in, because all of our catchments react differently because of their makeup, because of their characteristics, their slope, their soil, their geology, etc., etc. And they react in different ways, and we categorised that into 9 different types of catchments. So some catchments are right in the middle. If you have a change in rainfall, however you change that rainfall, you get a sort of one-to-one change in the flood response. But lots of catchments don't react like that. Some of them take a long time to react, depending on how they're made up, and that's what we call damped over there on your left. But some of the others, you add a little bit of rainfall, and you get a disproportionate increase in the peaks over here on the right, which we call sensitive. This is fine for 150. We had to work out a way of actually pointing at any catchment and saying, what would that one be like? So we came up with a decision tree type of way of doing that based on catchment characteristics, so that any catchment in the country you can place in one of these categories of catchment type. That I'll skip over. Then the next bit is about climate change scenarios. So for these 2 regions, northwest and southeast England, and for these 3 types of catchment in those regions, you have these different patterns saying how these catchments react to changes in climate. What you can then do is impose in this case, the CPO9 scenarios onto that, and then you get this cloud, if you like, this distribution of change according to those scenarios. So it tells you that this is the overall change. Say over here, for northwest England, neutral catchments, the overall change is like that. The CPO9 scenarios are that cloud there with a central estimate somewhere in those yellows over towards the left. But there is a chance that there's something in the red from those CPO9 scenarios. So when you come to get the CP18 scenarios, when they come out, you can just put those on this approach and see where we are and see how that cloud has moved. So that's the analysis that we did. We then had to address the quick, David. We had to address the science questions that we were asked to think about. So is the 20% any longer appropriate, and is it precautionary? So this analysis shows you, if you had these allowances along the bottom, so the 20% allowance there is indicated with the green line, and you compared them to the CPO9 scenarios, are you being precautionary, are you being safe? So the precautionary line, because on that axis it is the number of scenarios that are exceeded by this. If you had this allowance, then some scenarios would still exceed that allowance. So precautionarity is the 0 line. So if you follow the 0 line across, these curves all represent the patterns that you get from the different regions of the UK. So if you want precautionarity, you need this dotted line at the bottom, the 0 line, to be above all of those lines nationally, which means you'd be, I don't know what is next door, but we'd be next door before we got there. So a national allowance would be in the multiple hundreds of %. So if you want precautionarity, if you want to be safe, you need to increase your river flows by 200–300% and be safe against those if you want to protect against all future flooding, according to this analysis. So let's reverse it. That isn't something we can do. It's not what we want to do, and it's not financially feasible. So then we go back to the decision makers. So what's your risk? What risk are you prepared to accept? How many scenarios can you accept will be exceeded? If you had an allowance, you must understand that that allowance will not cover all eventualities in the future. So let's accept that decision is 40. If that decision is 40, then you can draw the line across from 40 and drop it down for each of the regions. So if you accept that 40% of your scenarios will be exceeded and you're in the red dotted region, then your allowance could be 20%. That's fine. But if you're in the blue dotted region, your allowance needs to be nearer 40%. And that's because of the hydrological makeup of those regions and what the catchments are like in those regions based on the analysis I talked about before. So all of this information came together, and these risk curves, as we call them, were presented to DEFRA and the EA and SEPA to come up with the guidelines that came out in 2011 and updated in 2016, which go an awful lot further than we had before. If you remember, before we had a blanket 20% for everywhere. Now we've got a range of changes expressing the uncertainty from the change factor to upper and lower estimates, plus a very high estimate. And we've also got numbers for different time periods as you go through the century. So that's, and for each region. So here we've got Northumbria. That what is a level of guidelines in terms of adaptation information that hasn't been seen anywhere in the, there have been things like this, but they tend to be much more broad brush. But anywhere in the world, this is quite, it's a bold step from the policymakers and the regulators. So that's described the research. What we're doing now with the EA and SEPA is developing a national tool that allows you to do this anywhere on the river network. So it's a point-and-click thing. It'll be a web-based thing where you can point at that red square there, and it will draw out the catchment characteristics. It'll define you a response surface. You can then put on your climate change scenarios, and you can develop your own allowances, if you like, within the framework of what we've done. So the CP1890 you could put in here, or you could put in your own scenario if you want to test something different. That's just started actually in the last month with developing this new web-based tool. So I've finished now, David, you'll be glad to hear. I think it's just thinking about, floods past, present and future. I think it's something we all love to talk about. The climate's something we love to talk about. And this goes way back to Samuel Johnson, who said, we live where we live, therefore we love talking about the weather. That sort of trivializes it. But we do live on where I said where we live makes it very difficult for these sorts of questions to be addressed, whereas it is inherently variable. Despite widely held perceptions, and I would say actually not in the scientific community, but beyond in terms of the press and even the politicians, there is no compelling evidence to suggest that long-term tendency towards increased severity or frequency of floods and droughts in the UK. We have seen some strange things happen in recent years, extended the extreme ranges of variability, as well as a very long and prolonged flood-rich period. And some of this volatility may be indicative of what climate change is bringing along. It could also be part of natural variability that we haven't recorded yet, and we have to not forget that. And then I finally talked about the research that we've done to support development of climate change allowances and support adaptation planning for flooding in the UK. Thank you very much.
So I'm joined by Nick and Chris now for maybe 10 minutes. I'm looking to Alan to see if we've still got 10 minutes. 10 minutes of questions and answers from the group. We have someone, man in the red jersey in the third row, just to the script.
I'm James Irvin from Cultibruggan Farm, next to the flood-prone village of Comrie in Perthshire. I'd like to ask the speakers to comment on the work of Professor Macklin at the University of Wales, and his extremely interesting and I think very well documented study using archaeological techniques, dating techniques, biological techniques, historical evidence, came to the conclusion that in fact there was plenty of evidence of very severe floods in the past, and his overall conclusion was stated as a history book can be very well written, very accurate, but it's not a lot of use if it only goes back 50 years. And he really undermined building too much confidence in the predictions that were told these days.
Thank you, James.
Well, perhaps have a first go at that. I'm not familiar with the exact paper you're talking about because there are several pieces of work, but I think I know the general work. It's clear from what I showed that there are floods in the 18th century in various parts of the country, and previously larger than we've seen in the recent period of increased volatility, whatever we would like to call it. So at the moment, we can't say that we've seen the evidence of climate change in increasing flooding above what's been observed in the past. So despite what a lot of people like to say, climate variability so far is larger than climate change in what we've observed. That doesn't mean that our future projections, as Nick's shown work here, are not credible, in that we have good physical reasons embodied in physically based climate and hydrological models to make predictions of what will happen in the future due to pretty well understood climate change processes. So just because we've had episodes of quite extreme flooding hundreds of years ago doesn't mean that we can't make predictions of what we expect to happen in the next 100 years or so. So I don't think there's anything exclusive about what Mark Macklin and others are saying about the future. It comes down to, are our climate models credible? Are they reliable embodiments of our physical understanding of the system? So the past is useful for validation of these, but just because we had huge floods in the past doesn't mean we can't make credible predictions of changes for the future.
Thank you, Chris. Nick, anything to add?
Yeah, I think you make a good point. I think you support actually what both Chris and I have been trying to say, which is there's a lot of data out there that we need to bring into our analyses to better understand our current flood estimation. And the use of historical data in flood estimation is something that we are doing. It was something that the National Flood Resilience Review had one of their main recommendations, that we should include historical data, not just the observed river flow records. So that's I absolutely agree. We're just completing with JBA a program of work for the Environment Agency, for example, on how you would do that within the flood estimation handbook type of techniques, and how you incorporate the uncertainty associated with some of these more these longer term historical records. So that's really important. I think it's very dangerous to flood estimation isn't done on a site analysis. It can be done on a site analysis. So I think we've got to be very careful not to throw out all the data. Just because we think we might be changing, because we think there might be some other data we could use, we can't throw out all of the data we've got. There will always be value in the recorded data that we've got. And we have to use that and blend it with other sources of evidence. And so, for example, in the FEH, we don't just use one site to understand what the flood estimation might be. We use data from a number of sites. We pool them together. We weight them according to their appropriateness for that particular site of interest, and then we develop a much longer time series upon which to base our flood estimation. So I'm personally very concerned about all the language around flood estimation after the recent events in 1516, that we can't tell anything from our data anymore. They don't mean anything, and they're too short, and all of this return periods shouldn't be mentioned anymore, apparently. And I find that all very difficult, and I think we need to have intelligent discussions around those sorts of messages.
Thank you, Nick. Yep, a question up next to you, Hannah, this gentleman. George Fleming.
Hi, my name's George Fleming. In 1966, I did the first flood frequency analysis for Scottish rivers and used all the statistics I could find. Then by 1971, I published a book on computer simulation and hydrology. And then in 2001, I was chairman of an institution of civil engineers commission on flooding following the 2000 floods. Nothing has changed. And each time we recommend something, it is put on the shelf for future consideration. I'm a civil engineering hydrologist. I look for solutions to the problem of climate change and, in fact, flooding of rivers. I spent my time in January of last year at the edge of the River Dee at Ballater, and was involved in trying to save the old castle, which we did. There's too much effort put into the assessment and not enough effort put into the solution of managing floods. And my appeal to this meeting is to focus a little bit on the solution rather than is climate change affecting the frequency of floods. I accept that climate change is changing the data, but we have catchments that have changed over the 100 years or 200 years. They've urbanized. The flood in the River Dee in January 2016 was caused primarily by accelerated snowmelt and very high rainfalls. As an engineer, I believe you have to look at the solution, but you must divert some of your resources to the solution and not always put your resources into the theoretical scientific assessment.
Thank you, George. I'll take that one then as working for SEPA, the lead organisation in flood risk management planning in Scotland, and agree with what George says, that we need to get on with the job. The Flood Act in 2009 precisely allows us to do that by taking a risk-based, plan-led approach to flooding, agreeing across Scotland where our priorities are and what our actions should be. But to do that without science is very difficult. To do that without an understanding of the current situation and the future situation is not impossible, but it means we might be directing our money to the wrong places. So we have to focus on what we know now, you're right, and get on with it, but also consider where is more sensitive to climate change, where we may find problems that we hadn't seen before, where we may have problems exacerbated by changes in flood series or by flood events. So the great thing about the Flood Risk Management Act in Scotland, it has that process in place. We have an agreed set of actions that we'll take forward. Some of them will be correct, some of them might not be, some will be achieved, some might not be. But we have agreed as a collaboration of organisations that we have a task to get on with. We're prioritising that, and government are putting money to that now. But to leave the science behind and to say we can continue to do that would worry me. We need to know that we're focusing on those areas in the future. And if anything, if the science flags up any new issues that we have, then we have to reassess and direct our attention to those areas. But so bringing the two things together, so what you're saying is correct, but we have a mechanism for getting on with that, and that requires science to deliver it. So that's nice. Any?
Well, just very briefly, I'm a civil engineering hydrologist as well, and I would say I spend considerably more time on design and solutions now and adaptation than on what I presented here. So I'd be very happy to talk with George later about what a university department is doing on practical applications as well as being guided by the science and understanding. It's both. You can't separate the two.
Yeah, well, I was going to say the same thing. When I was employed in what was the Institute of Hydrology, I was employed in the Engineering Hydrology Division. So a lot of the focus of what we do and what I tried to show in what we did was that, yes, it was a science exercise, but it was about a solution. It was about trying to provide the evidence for policy in this instance. And the policy is there to support the decisions that are being made. So I don't think we're not doing science for science sake. We're doing science because it is leading to solutions. So I think I take your point. The other thing I'd like to look at maybe is the amount of money that is actually spent on science compared to spent elsewhere on flood management. And I think it's probably, well, I would guess that is very, very small. So if you say some of the resources should be diverted from science to making things work on the ground, there isn't going to be much contribution, I would say. But, you know, we can have that debate.
Thanks, Nick. Time for one more quick question. Roger Crofts in the row number 5 or 6 there in the middle. Challenge for the microphone person.
Both of you have referred to, the headlines in the media, which the public accept. You're saying something quite different. And yet, people who have had their houses flooded, very often in recent years. What sort of message are you going to get over, and how are you going to get that message over, given the analyses that both of you have been talking about? Because that's really quite fundamental if we're going to change the mindset of people who are affected by flooding. Thanks.
Well, if I have a quick go at that one, I'm trying to get the message across to you guys today. That's part of part of the business. Myself and other colleagues are very happy and seek out newspapers and media to talk to. But if I characterise my message of caution and huge uncertainty surrounding these things, that doesn't sell newspapers. So I have a problem.
Okay. Yeah, I mean, our job as scientists is to present what we think we know and how well we know it. So we have to talk about the uncertainty, and that, as Chris said, that's a switch off. If you're talking to the media or if you're doing an interview and you start talking about uncertainty, they move you on very quickly. So it is very, very difficult. And I think our job is to always go back to the evidence, always go back to the science and what we do know. And it might not, and I understand it's not palatable. And if you've been flooded once, let alone a few times in the last few years, you want to know why, and you probably want something to blame. And it's not our job as scientists to provide that fall guy. It's our job to say, well, we don't fully understand. We don't fully understand natural variability. We don't understand extremes, but we're working very hard to try and understand, and we're working with the authorities to try and make flood management better so that you're not affected as much. So it's a really difficult message, because we do sometimes come across as naysayers when actually what we're trying to do is saying this is what we know and this is what we don't know. And both of those sides are really important for science.
Okay, thank you, Nick. Well, in the interest of time in session 2, I'll conclude there and invite Des Thompson to come up. But if you could thank the speakers again from session 1, thank you.
Thanks very much. Listen, we've all been sitting for a while, and I suspect travelling, so let's take 30 seconds just to stand up, stretch our legs before the next session. Give you a bit of a chance to get the talk ready. That's okay. Right, folks, if we can take our seats, please. Oh, it's always a mistake to say a minute, because people, of course, leave for various breaks. Thanks very much, everyone. We're off to a fantastic start. I'm Des Thompson, Principal Advisor on Biodiversity with Scottish Natural Heritage. We work very closely with SEPA, National Parks, various fora and Scottish Government in meeting the various challenges of flooding. A lot of our work is focused on meeting the 2020 challenge for biodiversity. And if I can have a plug on biodiversity, here in this very place on 10th, 11th October of this year, we will be holding a conference, putting a spotlight on biodiversity. So I'd urge all of you, please, to try and attend that event. Now we're going to move into predicting extreme rainfall. We've got two excellent lectures. First of all, we've got Hayley Fowler, our second lecturer from Newcastle University, who's going to talk about predicting extreme rainfall. Hayley works on the global picture of rainfall extremes and flash floods. So she's just going to give a tiny snapshot her research here, but I'd urge you to look at the speaker biography here, because Hayley's had a glittering academic career. She's raised more than £8 million worth of research funding and has given a number of prestigious public lectures. So we're really delighted to have you here, Hayley. And with that rather modest introduction, I'd like to invite you to take the floor.
Right, okay, thank you. So no pressure to give a good talk then, yeah? Okay, so what I want to talk about today really is not predictions of extreme rainfall, I guess, where I'd be talking about forecasting, but instead some of the work that we've been doing in various projects over the last 5 or 6 years now, which we first started doing in the UK, and we've now moved to look at changes in rainfall extremes more globally, under the auspices of the GWEX international programme on grand challenges in climate extremes. And this work's funded by various people. So, I mean, extreme rainfall is a big and perhaps growing, there's some debate about that, global issue. And you can see here that these are some very severe flood events that happened around the world, particularly in September 2013, when one of my big projects started in this field. I think we know quite a lot, though. I suppose what I'd like to do in this talk is tell you a little bit about 2 different types of flooding, which we haven't really touched upon so far, and in particular thinking about the differences between some of the flood events we've seen over the last decade or so, which have been very large scale events, things like Storm Desmond. This here shows actually the extensive flooding that happened in Brisbane in 2011, but of course we could be thinking about something like Storm Desmond, where we have very large amounts of rainfall over quite long durations, and we actually see flooding, quite extensive, widespread flooding in rivers. And you can see things like this, the road that collapsed in the centre of the Lake District, and of course extensive fluvial flooding. What a lot of my projects, however, have been looking at over the last 5 years or so is really something a little bit different, and something that we really don't understand as much about, both in terms of forecasting these types of events and in terms of the understanding the spatial aspects of that, and also predicting what might happen in the future in terms of changes to these convective extremes that happen in the summer, thunderstorm type events. This is a particular event that happened in Newcastle on the 28th of June in 2012. And of course, these events are also really important when we're thinking about flood risk. And perhaps, I'll say something in the talk about perhaps why we might expect these events to also increase significantly with climate change. And this is something we really don't understand very much about at the moment. And of course, they can cause quite extensive damage. This was to do with a collapsed, poorly maintained culvert, but you can see some of the damage caused here. And also, of course, these are the type of floods that are actually associated generally with high or potential loss of life. It's not generally the big, well-predicted extensive river flooding that causes loss of life, but actually these very flash flood events. This again is in Australia. This is in Toowoomba, which is just inland from Brisbane, and this again was in 2011. So before I start, I guess, in terms of talking about climate change, I mean, both the previous speakers have already talked about this, but just a plea really for, even if we can understand what's happening in the future with our climate models in terms of climate change, I think that we have not placed enough emphasis on actually understanding the baseline, understanding the natural variability of our climate. Now, that's a very difficult thing to do, as we've heard with the previous two speakers, but actually we probably haven't invested enough effort in actually trying to get to grips with how many of these big flood events have happened in the past, and actually trying to characterize more clearly the actual variability in flooding and in extreme rainfall in terms of some of the statistical methods we might use to actually start to plan and design and manage these flood events. Now, this is just giving an example from a project that I'm involved in, which is setting out to actually try and understand better the susceptibility of catchments to rapid response events, so rapid response catchments, particularly small catchments and particularly urban areas in terms of flash flooding. And the idea behind this project is also to then come up with better methods by which to forecast these type of events, which can be used by the Flood Forecast Centre and hopefully SEPA as well. David Archer's been basically looking at historical flood chronologies for a number of different regions of England at the moment, and looking at the odd event in Scotland. There's not been so much work done in Scotland. But you can see here, I mean, this clearly shows that basically, as the previous two speakers have said, if we actually look at the data that we have, we would actually estimate the 28th of June 2012 event as something like a 130-year event based on rain gauge data that we have. If we actually look, though, into the historical past, and David's done this by using newspaper articles and other types of historical evidence for various regions of the UK, and he's particularly focused on flash floods in this case, but you could do the same sort of thing for these very large, widespread flood events. We actually see that not only have 2 or 3 events actually exceeded the recent 2012 flood in terms of the rainfall amount at least, but actually we've had probably 6 historical events of similar magnitude in the last 200 years. So actually, you know, these things happen much more regularly than we understand from our very limited data time series. So that's one thing to say to start with. So I think that possibly we're not putting enough resource at the moment into understanding the variability in our climate and understanding this baseline as much as we're putting into actually understanding what might happen in the future. So a plea to everyone there. In terms of what's happening to heavy rainfall, I think some of this has been mentioned already, but basically all of the scientific evidence from various reports from the Intergovernmental Panel on Climate Change, things like the Special Report on Extremes, all points to the fact that the frequency of heavy rainfall is increasing over land. Again, our records are short. How well do we actually understand this in terms of trends? It's likely that this definitely seen increases in daily intensities, but also even in sub-daily, there's more indications of increasing trends than decreasing. Again, I think it's very difficult to say because your time series are so short. One thing they do say, though, is that it's likely from climate models that this heavy precipitation will increase over many areas of the globe this century. And of course, we know, again, if we look at past studies, and this only again shows that trends from 1961 here. So again, you're only really looking at that recent time period that Nick showed in one of his plots looking at flood frequencies, and we can see that flood frequencies have increased since the 1960s. Unsurprisingly, I suppose, rainfall extremes also have increased during that time. So we've seen recent increases in these very intense large, widespread and long duration events. But is that meaningful in the context of natural variability? We've had a number of different reports from things like the UK Climate Change Risk Assessment. Of course, the new one is meant to be coming out very soon. The UK climate projections, and I'll say something a little bit at the end about the new, what's happening in the new set of those that's coming out next year. But they all suggest that flood risk will increase significantly across the UK. And of course, I mean, again, as Nick was saying, this makes perfect sense, actually. So we've got this enormous amount of moisture available from the Atlantic. A lot of these very large-scale events are associated with what we call atmospheric rivers. They're large moisture plumes in the atmosphere that carry as much water, basically, as something like the Amazon River basin, or the Amazon River, rather. And they take, basically, moisture, if I can get this to work. You can see here, they take moisture from the Gulf of Mexico and just transfer this up, and you can see these plumes of moisture hitting the UK. And this is not a new thing. This is something that happens periodically and something that's likely to intensify under global warming, simply because of the increase in sea surface temperatures and the ability and the increase of temperature of the atmosphere as well, and their ability to actually hold more moisture. And Kevin Trenberth, who's a very clever guy who works at the National Centre for Atmospheric Research in the US, a very clever scientist, basically has said, and people have agree with this now, that extreme precipitation intensity should increase with temperature at this Clausius-Clapeyron rate, and that makes perfect sense. And he's got a paper out in Nature Climate Change this week, basically pretty much showing that for the reanalysis data and showing that forwards into climate models as well at a global scale, which is a very nice study. One of the things, though, that people don't understand is really what might happen to these shorter duration extremes with global warming. And there was this landmark paper in 2008 by a couple of scientists at the Dutch Met Office, basically where they really looked at some observations, hourly observations from the Netherlands, from De Bilt, a temperature, rainfall precipitation series at De Bilt, a very long time series of 100 years or more of hourly data, and they actually established that actually at the hourly scale, these intensities don't actually increase at the Clausius-Clapeyron rate, but they actually increase at something like 2 times Clausius-Clapeyron. And this, of course, is important when you're starting to think about impacts, because actually you're already seeing very large changes when you're talking about something like a 6 or 7% increase per degree of temperature rise. But when you're talking about a doubling of that rate, perhaps for something like flash floods, that actually then causes even more severe impacts when you're talking about flash floods. Of course, at the time, we were using quite coarse resolution climate models, and they really couldn't tell us anything about what might happen to these type of convective rainfall extremes. So another point that I want to make, I suppose, before telling you about these new climate models and their simulations, is that actually a lot of the methods we use at the moment to actually to basically design systems for managing floods are based on looking at annual maximum flood and annual maximum rainfall and relating the two. And you can see here, this is quite a nice study from Australia, actually. So they've looked at rainfall changes over the Greater Sydney region, and they've looked at changes from 5 minutes up to 48 hours, and then basically, this is looking at the changes in the maximum intensities, or the 99th percentile intensities. And you can see that actually the black line here shows you the change in the annual maximum, and actually that's increasing at the shorter durations, but decreasing at the longer durations. But basically, when you look at this seasonally, you can see that actually you see increases at all durations in summer and decreases at all durations in winter. So actually it makes quite a big difference actually when you start to tease out the seasonality of changes, So not only the seasonality of the extremes themselves now, but also the seasonality of the potential changes in extremes. And of course, you get different trends in different seasons, and this is again for Australia, but you could see the same sort of things happening in other parts of the world as well. And of course, this has quite large implications for planning, because small catchments could actually exhibit very different changes to larger catchments in terms of flooding. So these are the sort of issues we need to start thinking about, really, and being a bit more intelligent about the way we think about changes and the baseline we use to place those changes upon, I guess. So I want to move on now to tell you something about convection permitting modelling, which is what we've been working on with the Met Office for probably about the last 5 years now, with Lizzie Kendon and her team, a regional climate change team at the Met Office. So this is something that's commonly been used in the past for weather forecasting, and actually the UKV, the UK weather forecast model, is a convection permitting model. And we've got a lot of different processes going on, basically, in climate models, and you can see that different resolutions of climate models actually resolve different processes. So we've got global climate models, which are something like 100-kilometre scale, probably 60-kilometre resolution now, the grid cells, 60 by 60. Regional climate models down to about 12-kilometre resolution, so 12 by 12. And then we're talking about these, when we're talking about convection permitting models, we're talking about something that's at a resolution of less than 4 kilometres. The ones we've run over the UK are 1.5 kilometre resolution, so they're 1.5 by 1.5. So we're able to then resolve basically some of this convection that you can see here. And the nice thing about this is that we did the first study on this in 2012, but actually there's a number of other models that have now been run over different parts of Europe, over the Greater Sydney region in Australia, over Singapore, over the US. So actually we've got some other modelling studies to look at now and see what do these new type of models tell us about changes in future precipitation extremes. So, of course, the reason that we're interested in looking at these models, and this is a very old slide from a paper that published almost 10 years ago now with Marie Ekstrom, is basically because, and you can see this is the observations here, the UK Met Office observations for a winter 10-day 5-year return level event and a summer 1-day 5-year return level event. So even at the daily scale, these coarser resolution models, so this is a 25-kilometre resolution regional climate model, they can do pretty well at actually representing those winter extremes, those big, large-scale extremes like Storm Desmond, you know, so we can be relatively confident about their projections, perhaps, but they're very poor at reproducing these events that we see in the summer. And of course, part of that is to do with the fact that they don't resolve convection, but part of that as well is that actually once you get to 1.5 kilometre resolution, you can start to resolve the orography much better. And this is basically a nice slide from Andy Prine from NCAR, where he's basically showing the difference in model orography over the Rocky Mountains in Colorado. And this is moving from basically, basically it's moving from a 1.5 kilometre up to something like a GCM shows the Rockies as something like the end here. You can see it's almost flat, basically. So, you know, when you're thinking about the outputs from these kind of models and what it's telling you about future climate, this is what we're using. You know, this is why these models are able to capture more real features. So just some quick results. So, I mean, a lot of this work has been published already, but basically the nice thing about these models is that they improve the representation of the diurnal cycle of convection. You can see the observations in black here, time of day, precipitation. The red is the 1.5 kilometre model, and the blue is the 12 kilometre model. So we get the timing of these afternoon thunderstorm events much better represented within these higher resolution models. The other thing is that you can't really see these lines here, but when we, and thanks to Chris for explaining some of the extreme value stuff earlier on, but basically when we take the growth rate, and we see return periods here, for the 1.5 kilometre model is in green, and you can't really see it because it's actually overlying both the gauge data and the radar and the, just the gauge data and the radar. And you can see that actually the 12 kilometre model over-predicts summer 1 hour rainfall amounts in terms of return period. And this is because it has this problem of grid cell storms. So you kind of get a storm stuck in a grid cell, and it just rains and rains and rains and rains and rains. So you get these very intense events, but they're completely physically unrealistic. And, you know, that happens in the winter as well. So basically, because of these parameterizations, you produce very unrealistic spatial representations of storms and intensities of storms. And at the daily level, you can see, again, the 1.5 kilometre model is doing a much better job in comparison to observations. Again, there's a slight overestimation. It's less of an overestimation at the daily scale in the summer. And when you start to look at changes in the future from these type of models, that's when you start to get very large differences in their projections of change. So you can see here the 12 kilometre model projects very little change in precipitation extremes in the summer, whereas actually you get quite large changes from the 1.5 kilometre model. And this again is just showing the results over southern England, or Wales and England and Wales, southern UK. We've recently run a northern UK model, and it's kind of hot off the press, so I haven't got any diagrams to show you here, but basically it starts about here and the domain goes obviously north of Scotland. And just to say that basically from the southern UK run, the summer precipitation intensities are expected to increase by about 30 to 40%, but actually you get even larger increases in Scotland from this new run. And perhaps that's simply because we don't get many of these events at the moment. But hourly events over 30 millimetres show something like a 5-fold increase by the end of the century from this study. And we're actually using this work to provide guidance for UK sewer design in a UCWEAR project. So I've got only a couple more slides, I think, maybe more. You never know. So another thing we've looked at is basically how we can expect events to change in the future, because there was some observational work that basically said that as temperature warmed, events would become shorter and more intense. Actually, we take composites of all of the events over the 99th percentile, and you can see here that actually the red is the future, the blue is the present, and you can see some uncertainty bounds on this as well. You actually see an increase in the peak intensity, and you see a longer duration of event as well. And that, of course, over a time period basically causes a much larger event in the future. When we've looked at consistency with results for other regions in terms of these convection permitting models, the hope is, of course, that as we go to these type of scales, we will see less uncertainty in the projections of future change, and we can be more confident about numbers, you know, in terms of what changes we expect to see. So we were hoping to reduce some of the uncertainty. Actually, we do see some consistency. But one of the nice things about doing these studies is that we basically see some of the changes from the coarser resolution models, which are actually robust through the resolutions. So things like increases in wintertime mean rainfall, increases in heavy rainfall in the winter, and a large decrease in rainfall occurrence in the summer. They're all consistent throughout the resolutions. So we can be pretty confident that actually those things are real. They are happening in all those resolutions. But to actually look at changes in hourly rainfall in summer and extremes, and also this enhancement over steep orography and changes in rainfall duration, we need these high-resolution convection permitting models. This is the results from some of the work it's sort of hot off the press that we're doing with Uckwea. And basically, what we're doing is we're actually looking at proposing new uplift values by region. Northwest UK includes most of Scotland. Northeast UK includes a little bit of Scotland. But you can see that actually some of the high estimates are pretty big increases by the end of the century in terms of... but actually some of these figures are quite fairly consistent with what Nick was showing before in terms of daily changes. So I think convection permitting modelling can be very useful for all sorts of applications, and hopefully, well, the UK CP18 scenarios is going to include an ensemble of 20 of these models at 2.2 kilometre resolution over a UK domain. We're also running at the moment a European scale model in conjunction with a group at ETH Zurich as well, who are running the same model. They're a different climate model, but over the same domain, to actually look at what projections we get for the future. So I think I've said most of this already, but basically we can expect significant changes to future convective summer storms and enhanced increases in winter extremes. We get enhanced increases over orography from these very high resolution models. I think the important thing is that basically all national climate scenarios at the moment use these very coarse resolution models, which aren't able to represent the processes that I've been talking about in terms of convection. And actually, so we need to revisit these scenarios, and they're doing this with UK CP18 with this new ensemble of these type of models, because we could have actually significantly underestimate the potential changes in particularly summer rainfall extremes in the future, and we need to plan for these things as well as for these larger scale flood events. Okay, thanks.
Thanks very much, Hayley. Thank you, Hayley. Great to see so much new research hot off the press. Without any further ado, I'm delighted to welcome a colleague of mine within SEPA, Mark McLaughlin, to come and address us. And Mark is going to give a presentation on mapping flooding hazards. And Mark's got a highly distinguished in the field of flood risk management policy and planning, so we're delighted to have you here. The floor is yours.
Thanks very much, Des, for over-elaborating on my short piece there. Thank you very much. Very kind of you. Good afternoon, everyone, and again, thanks to the RSE as well for the opportunity to speak today on the challenge of speaking about the development of our flood maps for flood risk management. I do note that the RSE strapline is about knowledge being made useful, and it's important that we do recognise that our developing knowledge and how we present that has to be targeted towards true action to reduce flood risk, looking at the current situation and projecting into the future and what we predict for future climate change. So in terms of our flood maps, what I'll hopefully do for the next 25 minutes or so is just look back a little bit to where we've come from, consider some detail about the current state of our flood maps, and then look forward to how we're trying to develop those in future, particularly thinking about climate change impacts as well. So first of all, maps are not new things. They've been around for centuries. They've been cherished. They've been fought over. They've led to disputes across the world. They've also resolved disputes. But ultimately, they've been valued. They're valuable tools for conveying information, and we clearly want to be at that valuable and cherished end of things and not at the creation of disputes end of things with our flood maps. But what they give us generally is an understanding of our place in terms of our relationship to each other, and also in terms of our relationship to the geography, which ultimately influences our activities and our relationships. If we're able to then present that information clearly, then maps provide that opportunity to target our management of resources. All maps tend to have some challenges with them in terms of the quality of the input data that's used to create them, their projection, and ultimately ensuring that they're interpreted in the appropriate manner for the purpose that they were intended. So what does that mean for flood risk? Well, first of all, what do we mean by flood risk? Just to be clear, we look at flood risk as a function of the hazard. So the characteristics of the flood, in this case, that have the propensity to cause damage. And then we look at the characteristics of the things that could be affected by flooding. So the exposure, the number of people, the number of places, the number of businesses, the number of elements and activities that are exposed to that flood hazard. We also have to understand the vulnerability of those things in terms of their resilience or their susceptibility, but also their value as well. We tend to focus quite a lot on understanding the hazard side of that equation. It's what we've done, it's what we'll continue to do and understand, but we also need to begin to turn our focus a little bit more to understanding how those receptor data sets, those receptors will change across time as well, to give us that link between the hazard and receptor as we particularly look towards future changes and give us that true future consideration of flood risk. So fitting into that broad consideration of what maps give us, our flood maps will give us that indication of where might flood, the broad extent and consideration therefore of the likelihood of flooding. Allow us to understand what the exposure is, what is exposed to flooding. And if we can do that, and we can then use the maps to communicate what that risk looks like, it allows us that opportunity to assess and prioritise across the country to enable our management enable our management actions to ensure that we act and invest in the most appropriate manner, given the resources we have and given the level of risk that we understand. So when we're talking about improving our flood maps, we're ultimately talking about improving our flood models, and two broad ways of improving our models. One is improving the data quality input to that, principally looking at the hydrology, so how much water is coming into the system and draining into our rivers. And one is also understanding the nature of that topography in a lot more detail. And secondly, there's about improving our technique and applying the correct technique to the purpose of the particular study and what it is we're trying to achieve within the resources and constraints that we ultimately have in our day-to-day delivery. But what we're ultimately trying to do is improve our confidence. We want to improve our confidence in those models, and if we can reflect that in our maps, we improve our understanding of what that flood risk is, and we can be much more confident in our decision-making about where we target our investment and our actions to reduce flood risk. So we've got records going back centuries, but it's only the last 20, 25 years or so that we've been explicitly using flood maps to support the delivery of policy. So looking back a little bit towards the 1990s, we had the Institute of Hydrology 130 map. This was used to inform land use planning policy at that time. It provided only a fluvial consideration for the 100-year return period, but it did give us some extents and depths. Looking back at it now, although it was a very good tool at the time, it does appear now rather coarse, and it did only give us the broader watercourses with catchment areas greater than 10 square kilometres. Recognising the need for development in the early to mid-2000s, the indicative river and coastal flood map was developed by SEPA between 2004 and 2006. That introduced an additional coastal source in addition to fluvial source and 3 return periods, although admittedly only one of those return periods was actually published. It gave us extents and extended the reach of those flood models and ultimately our mapping outputs to catchments with areas greater than 3 square kilometres. So it gave us a big step forward in that sense, although we kind of lost the hazard side of it in terms of depth. So where we are now, we've taken a massive step forward since those times. We now have 3 flood hazard sources: rivers, coastal and surface water, for a range of return periods. 3 of those are published on SEPA's website at the moment to deal with the requirements of legislation. We also have explicit risk maps which take into account the impacts of those hazards on receptors, considering people, communities, businesses, environment and cultural heritage. And although it's not shown here, we also have maps that indicate areas of potential for natural flood management application as well. So building that wider catchment-based consideration of flood hazard and risk, developing that understanding to ultimately target towards management actions to reduce flood risk across the country. So that massive change in volume and scale and scope of understanding of flood hazard and flood risk has clearly been instigated by developments in policy, principally the Flood Risk Management Act, but supported by flood risk management guidance. We're implementing and have implemented a much more holistic catchment-based approach to flood risk management. And although there are clear requirements to deliver within that legislation, one of, or arguably the most important part of that, is the clear framework to allow collaboration, explicit collaboration between authorities to target towards a single duty to reduce overall flood risk. So with that single target, we're all beginning to work towards and have made some significant strides towards working towards our improved understanding. And as we improve our understanding, we're able to share our data and information much more readily. But it's important that that quality of information is also raised so that we have that confidence developing, and also so that across those different agencies, as those different projects are delivered, they can all fit into a single national product. And to that end, SEPA published in the last 12 to 18 months its flood modelling guidance for local authorities that will enable outputs from their studies to be input directly into SEPA's modelling flood maps much more readily, and vice versa, our data can be provided much more readily to support local authority studies. So very briefly, just a quick overview of the flood maps. In terms of the fluvial flood maps, we ran 9 return periods, looked at defended and undefended runs. So within the maps, we do have a consideration of formal flood defence schemes based on information contained in the Scottish Flood Defence Asset Database. And we've also undertaken some climate change scenarios, which I'll touch on later on. We have flood extent, but we also have depth and velocity information across the country. And we've utilised, where we've got good quality DTM information in the form of LiDAR data, more detailed model resolutions, principally in those urban areas, the most populous areas of the country. However, as with any modelling study and any mapping output, there are limitations. We delivered this study alongside coastal and fluvial studies in a period of 2 to 3 years at a national scale. It really challenged the capabilities and resource processing power available to do that. And while we managed to make those achievements, we do recognise that it is a broad national scale approach. The hydrology in particular needs some further refinement, although it was checked. It was informed by the CH flow grid. It was checked and ensured that it was within certain bounds based on SEPA's recorded gauge data. But there's clearly scope there to be more specific in how we represent hydrology. And as with all elements, the more information we can get on the topography and the nature of structures will ultimately help us understand better where those hazards and where those risks will arise. The coastal flood map hasn't evolved in the same way as the fluvial maps. It's still based on a projection modelling method where sea levels are determined and projected on land onto a DTM, with the assumption that all land below that level is therefore at risk of flooding. That again has its limitations. There's no dynamic element to that. It's a straight line projection onto the topography. And there's clearly a potential to overestimate where we have structures or features along the coast to assume that they're having no function whatsoever in terms of flood hazard or flood risk management. But crucially, we're not taking into account at this stage wave impacts, and I'll touch on that as a major development area in a few slides' time. For pluvial flooding, I reference here something that we call regional pluvial. That's to differentiate it from a national pluvial study that we did back in 2010. That gave us a broad overview for the entire country, but recognising that we needed more detail to meet the requirements of the legislation and to support the delivery of appropriate actions. We've undertaken more detailed analysis where we have that quality LiDAR data. So principally shown here, the most populous areas of the country again, so the major conurbations. So we've got a detailed DTM, again a fairly high resolution modelling, a range of modelling outputs, again, consider a range of return periods, but also look at a number of different storm durations as well. So looking at something that Hayley touched on there about shorter and longer term durations and their potential impacts. So again, the inherent limitations or uncertainties around undertaking a national study where we've made some broad assumptions about losses and about the role of individual drainage systems, and about the durations, not necessarily looking at catchment or critical durations, but looking at broad durations. So clearly, there are areas that we will look to develop in the future. So that future direction then, again, looking at each of the sources in turn, we recognise that there are immediate actions that we need to put in place to support the delivery of flood risk management plans and strategies, but there's also a longer-term intention to strategically develop our flood maps across time. And we've targeted a number of the major catchments across the country, and we'll be seeking to improve across those the representation of the channel and the topography, the hydrology, and looking at more detailed modelling analysis. So it's a massive investment in data. Colleagues at SEPA are managing these particular projects at the moment, and a number of these have been completed. Some are out, some are still to go out for tender. But ultimately, we're investing upwards of £170,000 in survey to obtain good quality information that provides us a bank of data to feed into updated and improved modelling, which we should see that improvement in confidence and quality coming through into new series of maps and as we progress into second and third cycle for flood risk management reporting. In coastal, I identified that there are clear areas that we do want to develop. We're working with the EA and others on updating of the coastal flood boundary data set, so that will give us improved and updated design levels around the coast. But there's a real drive and a real wish and willingness to incorporate more dynamic modelling within those, and particularly understand better the impact of waves at storm events. So again, another huge data investment, but if we can invest that in an appropriate way so that we are obtaining multiple benefits through delivering on our flood risk management activities in terms of modelling and mapping development, but also supporting development of flood forecasting and warning schemes, then we're getting some degree of additional push for the money and investment that we put in. So again, in terms of pluvial flooding, there are a number of internal drivers that we recognise right from the off, principally around understanding the relative appropriateness of durations, what is the most appropriate duration to use to inform flood risk management strategies, but also around about how do we better understand the losses, how do we improve the runoff models in those particular areas, particularly in urban areas, and how do we understand better the role of subsurface drainage? How do we link better with Scottish Water models on sewer flood risk assessments and integrated catchment studies to better understand and bring together the sub and surface analysis into something that's much more coherent. But there are external drivers as well, and that principally in the form of updates to the FEH13 DDF outputs, which indicate significant increases in design rainfall, particularly for short duration and high frequency events across Scotland. So clearly a driver there to be reviewing and understanding what those impacts mean, not only in the maps themselves as they require, but what does that mean in terms of implementing flood risk management strategies, and in particular surface water management plans. So those are some of the kind of technical elements that we're looking to develop and improve, and that will go on. It will not necessarily be complete within the next cycle, but there's a rolling programme and a target of improvement and delivery across our reporting cycles. But ultimately, our best way of understanding flooding mechanisms is witnessing and capturing information from real flood events, and using that to feed back into our models to calibrate those and improve the confidence that we have in those. So there's a great opportunity there to get out in the field and obtain good quality survey if we can deploy rapidly in the field. So to that end, SEPA's developed a tool to utilise in the field. We've called it Flood Event Data Capture Tool, or FEDCAP for short, because everything needs a nice handy acronym. Ultimately, what that provides is being loaded onto a tablet or onto a phone, taken into the field, that will allow immediate georeferenced data that can be fired back into the database almost immediately. We've got a standardised system of recording impacts of flooding, so we record that on the same device, and ultimately we're getting towards a position almost of having real-time uploading of flood event information in the field in a consistent and detailed manner to support the delivery of flood risk management. So what that ultimately means is we get more people out in the field. They only really need to take a phone or a tablet, get out in the field. They don't need to be a flooding expert to go out and do that. They need some training perhaps on how to use the tool, but they can get out in the field, record the information, fire it through the cloud. It's downloaded directly into SEPA systems, and we are able to then analyse that information much more readily and feed that directly into our systems much more quickly than we've ever been able to do before. So we're getting good quality information almost at source, recorded almost immediately, and able to feed that back into our modelling and mapping processes. We had a plan to do that at the beginning of the last flood risk management reporting cycle, but we brought that activity forward so that we were in a position for the winter of 2015 to give a nice little safe trial of the product. And then we were obviously hammered for most of December and January, December being the wettest month that we've had on record. 1,000 properties affected by a range of storms and a range of flood waves that hit us, and other speakers have already spoken about this morning. So there's a great opportunity, masses of data to go out there and test. So on that side, really good once we got past the initial urgency of flood forecasting and warning duties and support for emergency response. But what that trial demonstrated is that the quality of the survey information was good by comparison to more traditional survey techniques, that we massively reduced the amount of time spent in capturing that information in the first place. We captured much more information, and it proved that in capturing that good quality and consistent information across the piece, we're in a position to think about rolling that out more widely across SEPA to non-flooding staff. And in discussions with local authorities and other agencies and Scottish Government, there is interest in the utilisation of that particular tool. So again, we can widen that scope of capturing that good quality information, all feeding back into improving our knowledge and understanding, which ultimately feeds down into defining and targeting our actions and investment in flood risk management. So, as I mentioned earlier, we have considered within the current flood maps climate change. Again, it's based on information that Nick already spoke about. There's a specific study to fill the gap in Scotland of understanding the sensitivity of catchments to future change. At the time, we were able to identify a high emissions scenario, 2080s time horizon, and look at the 67th percentile. So looking at the change in threshold that was unlikely to be exceeded. And although we haven't published that information yet, it is embedded within our flood risk management strategy. So we are looking to embed climate change within the actions that we're putting in place. But it's important to recognise that that's not an academic exercise, it's a real need. If we want to really embed climate change and really deliver real reductions in flood risk across time, we can't stand still. We have to keep ahead of that impact curve as a result of climate change. So with 108,000 properties at risk at the minute, if we do only do what we've set out in the last strategies, another 60,000 properties could almost naturally come into the flood risk category as a result of climate change. So it's essential that we do look forward and we do build that into our modelling and mapping to inform our future strategies. So to do that, we are looking to develop a greater range of information, a different extent of climate change scenarios. And to that effect, we are working in support of a number of studies, including working with the government user group on UKCP 18. Nick's already alluded to this, so a familiar couple of slides. We're working with the EA on the development of and refinement of that climate change information that we've had since 2010-2011 into that higher resolution grid across the country. But as part of that, we're also looking to update our knowledge and understanding of changes in mean sea level towards the end of the century and potentially beyond as well. So we're able to then support that understanding of future state. And if we're able to consider what that future state looks like in relation to different climate scenarios, we can begin to understand, well, what does that actually look like in terms of future flood risk? So if we get our hazard and our receptor data sets moving together across our different time slices, what does that future look like at 2100? That allows us then to think about our ambition as a country in terms of what do we want to target our action to reduce flood risk. Do we want to be a 4-degree country or a 3-degree country in terms of providing that target range? So that's not going to be easy, but if we're able to develop that kind of system and develop that kind of approach that gives that future target, then we're able to then track our investment and track the effectiveness of flood risk management across our reporting cycles and aim towards that true reduction of flood risk in the future. So I've touched on some of the development. Clearly there are other things that we'll be looking to do. If we can improve the national picture of LiDAR information, that'd be great. High-resolution topographical information is clearly a significant element and a significant driver to improvements in flood modelling and therefore flood mapping. We do need to understand better the effect of structures, so including those formal flood defence schemes, but also those other structures that have some sort of flood role, even if they were not necessarily designed for that purpose, and what is the impact if those things were not maintained or they were removed. How would that change overall flood risk? So there's a lot to do there. There are clearly developments in modelling, and we need to keep tabs on that and work with academia and other research agencies about how the modelling opportunities are developing in time. There are opportunities as well to link flooding and erosion. There's work on the NCCA, the National Climate Coastal Change Assessment. There are outputs from that that clearly can support the delivery of flood risk management strategies. So how do we bring both the modelling and the erosion and flooding elements together? But I think critically it is about understanding that future state and defining that target much more clearly and defining that overall continuum of development and reduction in flood risk over time. So what does it all mean? And it has got to mean something. So to get back to that strapline of the RSE, it's about knowledge made useful. It's got to be useful and usable information at the end. So by improving our modelling, improving our mapping, we improve our overall understanding of flood hazard and risk. And if we really improve our understanding, we improve our confidence, and that gives us more confidence feeding into the development of the next series of strategies, these evidence-led plans that set out sustainable actions for flood risk management. And we can be much more confident then about where we prioritise our action and where we prioritise our investment on that risk-based approach. Ultimately, we're aiming at having fewer people, fewer communities at risk of flooding in the country, and thereby ultimately defining and ensuring that there is continued confidence in Scotland and that social and economic development in the country continues unabated by flood hazard and flood risk. So our flood maps are available on the website if you do want to look, if you have not looked at them before, so they're accessible on the website. So thank you very much for listening.
Another super talk. Thanks very much, Mark. We've got time for a couple of questions. James, we've heard from you. Can I just see if we've got any other questions? Yes, sir. Just hold on till you get your microphone. Thank you.
Ian Griffin, JKS Engineering. It's a question to Mark as to, does SEPA have any long-term ambition to provide a flood product in a similar manner to the Environment Agency, which gives consultants a greater tool to assess flood risk and access to the data that they hold?
A specific product is not set out at the minute, but we do recognise that we're sitting on a massive amount of really useful information that we're challenged to get that out there to make it useful. It's got to be usable and it's got to support all the actors who are involved in flood risk management. So it's not only the responsible authorities, the local authorities, Scottish Government and all these agencies, but it is consultants and it's the public as well, because there's a public ownership element of, or public responsibility element in terms of individual action. So we are working towards making our data more available. There is an ambition that we are able to have a kind of portal or one-stop shop for flood hazard and flood risk information that would enable people to come in and extract that information and utilise it and analyse it as well for their purposes, but also feeding back into the system and into the process that we're working on. So it's something that we are looking to develop. Whether we get to a product similar to the EA or not, I don't know at the minute, but we're working on the same kind of trajectory of making the information much more readily available and support that wider flood risk management work.
Thank you, Mark. Haley, do you want to comment on that? Fine. Great, super. James.
Yeah, James Evan, Cultibragan Farm. Yeah, I do really have to take some issue with you. because I'm not alone among the many farmers in Scotland that are deeply concerned at the attitude of SEPA towards the management of the rivers. And there seems to be a serious imbalance between the need for biodiversity, which is in your remit, water quality, which is in your remit, and flood warnings, but there seems to be a sad lack of pragmatic management of a river. And you're looking for knowledge. You've got knowledge by people and the landowners who are the guardians of the landscape for years, right? And it's interesting that not one is represented in this meeting's program. Now, what's happening, actually, is because SEPA's rules came in about 1990 or something, in which extraction of gravel could not be done. It was done by the responsible farmers.
I'm going to stop you. James, I'm sorry, I'm going to stop you. I'm going to suggest that the two of you discuss this over lunch.
Well, no, this is a public issue. This is a public issue, sir.
It is, James, but
and
we're
the
talking
obvious
about
thing is to remove some of that obstruction which is there and blocking rivers. You can have as much data as you like, but the pragmatic management is staring you in the face.
Okay,
remove these obstructions and you have far less flooding.
Thank you. All right. Thank you, James.
If I just touch on that generally, thanks very much for the detail. And you're right, there are people who manage the land, and there's a whole host of information there. And I think across the number of the talks, we've talked about historic information, we've talked about recorded records, but it's those records that are left by people as well that provide the detailed knowledge of individual catchments and where they are. And we have a series of groups established. We engage widely across a number of national groups. We have regional groups established that we engage with a range of organisations and public and community representatives, with Scottish Flood Forum as well. And we utilise those to suck in information as well as impart information of where we are. So we see it as a two-way process to ensure that we do build that development and develop our understanding and knowledge in the catchments. On the specific issues of land management, I think I recognise the challenge and the issue that you've flagged, and that's certainly been flagged before. And I think in the last 12 to 18 months, we've gone a long way towards working much more closely with land managers to make some developments. There may be some work still to do there, but I think we're beginning to improve those relationships, and I think looking at making those sort of multiple benefits within catchments are something we'll continue to target.
Thank you, Mark, and thank you, James. That's a very comprehensive answer, and I hope you can carry on with that over lunch. Are there any time for one more question? Yes.
Thank you. Gary Pender from Heriot-Watt University. I had a question for Hayley, actually. Your presentation focused very much, as far as I understand, on grid resolution being important as far as capturing some of these convective cells was concerned. Mm-hmm. But can you just advise me, is there any sort of updates or new numerical techniques or modelling techniques that links in with the type of stuff that Mark was talking about academic improvements to their modelling capability?
I mean, it's not just grid resolution, I guess, that's changed within these models. So we've got higher resolution models, but we're also no longer parameterizing convection within the models. So basically, I suppose when you're running these type of models over coarser resolutions, so say 12 kilometers by 12 or something like that, because a lot of the processes happen on much smaller scales within reality, yeah, you actually have to, what we call, parameterize those processes. So you basically make, you basically make some, you write equations that basically characterize those processes over those, as an aggregate, over those larger scales. So what we're doing with these newer models is actually basically representing convection directly within the model rather than actually parameterizing it over the larger scale. So there are differences within the modeling system itself, not just the resolution. I think one of the nice and interesting things that we've been able to do as part of this work is work much more with the forecasting community, actually, because I think the climate modelling and the forecasting community have historically just worked quite separately. And because we're now using the forecast model and it hasn't actually been run over these long timescales before, and there were a whole load of issues that we were able to resolve with the model before we were able to run it over these longer timescales anyway. But actually, a lot of the things that we found and deficiencies in the model, they've actually been able to go back and think about it in the forecasting community and actually come up with some solutions for these as well. So I think it's a kind of two-way feedback thing as well. So hopefully a lot of the work that we're doing in the climate modelling world will actually improve the forecast model as well.
Thank you very much, Hayley. Any more questions before we break for lunch? I'm making sure we give everyone a fair say. No? Would you please join me in thanking the two speakers? Thank you. Now, Alan has a brief announcement.
Just before we break for lunch, Marjorie Roy from the Royal Met Soc has asked me just to draw to your attention their next meeting. On Tuesday, the 21st of March, there's going to be a lecture on forecasting Storm Frank by John Mitchell of the Met Office in Aberdeen and Louise Parry from SEPA. I think, given what we've already heard this morning, that seems to me highly appropriate as a follow-up event to this one. 21st of March, 6 p.m, Institute of Geography, University of Edinburgh in Drummond Street. We're running a little bit late for lunch, but lunch will be served upstairs in the welcome rooms. And can you please be back here at 20 to 2 for the afternoon session?
Okay, hello everyone, welcome back from lunch. My name is Sarah Hutchin and I'm chairing the start of this next session on flood risk management and in particular in relation to adaptation and resilience. I'm Senior Advisor on Freshwater Policy with Scottish Natural Heritage. I've been involved in the development and implementation of the Flood Risk Management Act and an inclusion in that of consideration of natural flood management measures in flood risk management. The SNH obviously is interested in the contribution that NFM measures and green infrastructure can make to flood risk management and also the additional benefits that they can provide for biodiversity and for creating attractive places for people to live and work. So in this session we've got two presentations on how we can manage catchments to reduce flood risk and how we can make our cities more resilient to flooding. So first we've got Professor David Barnforth, who is an Executive Technical Director at NWH. His recent work ranges from the oversight of multi-million engineering programmes to flood advisory work in UK, Singapore and New Zealand. He's also a visiting professor at Imperial College and a past president of the Institution of Civil Engineers. David, would you like to come up?
Well, thank you, Sarah, and good afternoon, everyone. Thank you for inviting me. It's a great pleasure to be here. I'm going to talk about urban flooding. And to illustrate this, the Glasgow 2002 floods. Urban flooding is a very complex process. This analysis done by Scottish Water at this particular location showed that of the flooding here on the ground and within property, 1,500 cubic metres came from local rivers, 800 cubic metres from the public sewage system, and 1,200 cubic metres directly from urban overland flow. This is rainwater that falls on the ground, never gets anywhere near a drainage system at all. It just contributes directly to flooding. And managing that complexity is very challenging. And our conventional approach to this, of course, is to try and stop this flooding from happening. So we invest ever more in large infrastructure, more sewers, bigger pipes, tunnels, storage shafts, and so on. But if we set that in the context of the future, we have to question how sustainable that approach is likely to be. So this is just a simple pie chart which looks at the flows that are generated from urban runoff for existing scenarios, for existing extreme events, and then taking into account the sort of factors that are going to influence that in the future. Growth, which is shown in red, and this is assuming that that growth goes ahead with appropriate SUDS installations as part of that growth strategy. So this is assuming that there's already some inbuilt storage into that new development. Then there's urban creep. This is the infilling of urban areas in between existing buildings without any real major development, but nevertheless it hugely contributes to runoff. And then, of course, the ever uncertain climate change prediction, which we've been talking about this morning. But what is really interesting is when you look at what might be the implication of something of the order of a 40% flow on our urban systems, then you see what was described this morning by Nick as a sensitive catchment response, because the response is by no means proportional. That 40% flow will typically generate 100% more flood volume on the surface, 130% more properties that are affected, and a 200% increase in flood damage. That's a threefold increase in flood damage by the year 2080. These are all 2080 predictions in very general terms, and we recognise the uncertainty associated with that. But what is worse is that if we carry on with our conventional approach, our solutions costs for this, our means of managing this with conventional infrastructure methods, would see costs rise for somewhere between 4 and 8 times. And just to get the uncertainty bit right, I don't think it matters whether it's 4 times or 8 times, actually. It's completely unaffordable. What this demonstrates is we simply cannot continue with our current approaches to managing urban flood risk. Now, that doesn't mean we don't have to continue to invest in conventional measures. We do need to continue to invest in storm drainage, but we have to recognise, both professionally and publicly, that there's a limit to that, and beyond that limit, flooding will occur. And it's likely to become more frequent, and it's likely to become more severe in the future. And we need collectively, as a society, to learn how to manage that flood by adaptation and resilience. So I'm going to say a little bit more now about what that might look like and pick up some examples from projects around the world. And the best way of structuring this is to recognise what is becoming much more widely accepted now as the 3 elements of drainage, which is a source, pathway, receptor concept. And we need to start looking differently at how we manage in those 3 areas. So firstly, limiting the flows that get into our drainage systems to enable them to do more work than they're currently doing. Then to recognise that flooding will occur, but instead of just leaving that to random chance, let's look at how we might manage that by creating surface pathways to manage the flows that exceed the capacity of the drainage system, to direct those to sacrificial storage areas in our urban areas where the damage from that flooding will be far less than if we just allow it to be indiscriminate. And then finally, to improve the resilience of those parts of our urban areas that get impacted by the flooding, the receptors. This will be properties, infrastructure, and so on. I'm going to give some examples of how we might do that. So let's start with that source control, limiting the flows entering the drainage system. So the first picture here on the top left, I've deliberately chosen pictures rather than graphs and numbers this afternoon. I slightly apologise for that, but I did have in mind this was the first presentation after lunch, so perhaps we'd make it a little lighter and less demanding from that point of view. But this is an example from Portland in Oregon. Now, in Portland in Oregon, the domestic dwellings there, which contribute a substantial amount from roof runoff to urban flooding, are fairly well spaced out. And what they did in Portland was they put in place a customer incentivisation programme. So they incentivise people to disconnect their roof areas and to drain that runoff onto the land surrounding their property so it could naturally infiltrate into the ground. Now, what is interesting about this project is that incentivisation programme, which wasn't a large financial incentive and it was supported by the formation of local self-help groups, resulted in an 80% success rate in rainwater disconnection from roofs. And that's a remarkable achievement. I think actually that project there is more important in terms of the lessons from community engagement than it is from the actual measure that was used in that particular example. Retrofitting rainwater barrels, something I'm personally very keen on. I've done some work on this in the past. I've piloted this, works very effectively. Of course, for Storm control, these barrels need to be empty rather than full, which is why we've not called them water butts. Also, I do tend not to use the word butt very much when I'm working in the Americas. It doesn't go down too well, and it tends to be largely misunderstood. Project we delivered some while ago in the Netherlands on the left here is a retrofit infiltration basin. Now, this takes water from an existing urban development. It's been retrofitted into a park area, so this will be covered over and regrassed afterwards. And this takes the water, it stores it in there, and then it releases it slowly through a borehole into a deep aquifer. So it also acts as an aquifer recharge system. So you're actually you're short-circuiting the water cycle locally, primarily to manage drainage, but also to act as a water resource. From an adjacent area, so that was from Delft in the Netherlands, not far down the road in The Hague. We've got this example on the right, which is source control as part of urban regeneration. So this is using the opportunity of a general conversion of what was originally an industrial area into a dwelling area, a domestic dwelling area, and the retrofitting of source control basins, small basins there, just to compensate for the acceleration of runoff that occurs when we urbanise areas. So it's to return the runoff characteristics of that area to what it would have been like before the development had taken place. So once we've addressed the source, we can now move on to the pathways. And I'm not going to talk here about enhancing the capacity of our drainage systems. What I'm going to be talking about here is how we manage those exceedance flows on the surface. Now, we know from our experience of modelling and mapping, we actually can predict pretty well now where flood water will go in urban areas. We can identify, and we can colour code if we want, as we have here, the properties that are affected. But what's really important here is working out where the flows will go, because interestingly, what we find with urban floods is that water tends to flow downhill and accumulate in low spots. So here it is, in the 2002, Glasgow floods, road acting as an exceedance flood pathway. Highway engineers say to me, oh, we can't do this. No, we mustn't do this. And town planners say, we don't want to see this. I said, but you've got it already. This is not something we're expecting to happen every day. But in your really big rainstorm events, you will find that a considerable volume in urban areas is transferred like this on the surface. At relatively small depths and modest velocities, but it does convey large volumes, and it usually dumps it just where you don't want it. In this case, about half of this flow went into a leisure centre and caused a huge amount of damage. And we could have managed that, actually, if we were more creative about creating these surface flows. So here's an example from Cornwall of a road designed as a flood channel. The people of St Blaise were fed up of getting flooded by their local watercourse in extreme events. The road tended to get flooded in the same time, but basically most of the flow from the catchment went into the watercourse. It then went down a very narrow channel to the village, and it caused flooding. And it also flooded the local petrol filling station, and the owner of the petrol filling station came up with this idea of saying, well, why don't we just keep it on the road and divert it on the road around the village during these events? And the engineers, local engineers, said, okay, we'll have a go at that. And they designed this. And this is a road here which acts as a flood channel in extreme events. You can see the spillway into the watercourse downstream of the village. So now, instead of the village flooding, the road floods, but at a modest depth. Traffic's limited to 30 miles an hour. And it works remarkably, and remarkably well. On the left picture here, we see we're back to that urban regeneration in the Netherlands, and here we see a drainage where the surface water is kept entirely on the surface. There are no surface water sewers on this development. All the rainwater comes off the roof and off the surface area, and it flows into the road. And the camber goes the other way on the road. It has a channel in the bottom, and that conveys the water under normal storm events, and then the more extreme events, it fills up. The whole of the road then acts as a flood channel, and that then can overflow into that infiltration area you see in the background there, and then that in turn can overflow into the woodland, which becomes a sacrificial flood area in the even more extreme events. And again, I've had other engineers say, well, we can't do that. We can't have the camber going the wrong way on a road, or this channel in the middle of it. People will trip over the channel, or what. It works fine. It's just an estate road. It's not the M8 motorway that we're talking about here. So And then similarly, the swale from this development here, which is very effective for modest runoff, functions as a conveyance and a water treatment facility, but under extreme events, the whole of that grassed area fills up to provide a conveyance channel. But I think my favourite example of creating exceedance flow channels in urban areas is the Connswater Greenway project in East Belfast. This is a deprived community, a low-income community in East Belfast. It doesn't have much amenity, and it has what you often find in these areas, a canalised watercourse full of rubbish. And a local community group got together with the idea of creating an amenity park, a green corridor in this area, which the local residents could enjoy. And they called their first public meeting to put this idea on the table, and the local residents said, "Oh, so you've come to fix our flooding problem, have you?" And everybody went, "What flooding problem?" And of course, it turned out that this watercourse was not only an eyesore, but it actually flooded. So flooding also became a driver behind this. And if you look at these two pictures, the top picture here shows the watercourse. It's on the boundary between the green area there. It's just that little ribbon. Let me just see if I can avoid the nervous shake, of the pen here. And just like that, there's the Connswater Greenway. This is the estate here with fairly high unemployment, low-income families living on there. And this is the realigned waterway, meandering natural waterway. But what they've also done is between this footpath here and the boundary on this side, they've created an exceedance flood channel. So the whole of that area now can be used to convey flood water and reduce flood risk. And it's a really imaginative multiple use of the area. I'm going to come back to talk about that in a moment from the amenity and recreation point of view. Here's a very similar concept in a new development in Singapore. This is in the northeast area of Singapore, where there's a lot of new housing development going ahead. Similar watercourse here. And this is just to give an example of marking out the exceedance corridors so that people know what to expect. They know it's meant to fill up in extreme events up to the level of those markers there. So there's a management of expectation in the community. Sacrificial storage, all sorts of ways we can do this. This is two examples. The right-hand picture is from the town of Malmö in Sweden. Peter Starr, who was the chief engineer of Malmö, was a real pioneer of sustainable drainage and some of these other techniques. And at the left from a city in Brazil, and it was a big open square like this. Reminds me a little bit of George Square in Glasgow. This fills up with water in times of heavy rainfall. We've not quite managed to achieve that in Glasgow yet in George Square. And it is a challenge, isn't it, for municipal authorities to actually say, we are going to deliberately flood this area in preference to this area. Don't think we've really crossed that bridge in our municipal planning in the UK just yet. And then finally, the resilience of receptors. I do some work on a regular basis in Singapore, advising on flood risk management. And Singapore have some very interesting, very simple, straightforward rules on minimum threshold levels. All new build, including infrastructure, has to have a threshold level for all entries, whether it's a ventilation tube or it's a pedestrian access, 1 metre above the level of the surrounding maximum flood level or the surrounding ground, whichever is the greatest. So the picture on the top left is a new shopping mall on Orchard Road in Singapore. The bottom picture, one of my favourites, is the entry to the metro station on Scots Road. It's the new standard design for metro stations in Singapore. Most of them are built like this now. So you actually go up a flight of steps or a ramp or a small escalator onto an entry platform, and then you go down into the metro. So in the last 3 floods, which they have had in the centre of Singapore, not only is the metro operated, it's actually operated to time. As opposed to the metro here, which was suffering rather badly in Japan, in Tokyo. This is what happens when you have a level entry to a metro system in a flood event. It's an interesting behavioural reaction from the public here. I certainly would not be taking a small child down into this metro. But this is a big worry, for example, for Transport for London, where most of the London Underground entrances are at street level. Doesn't have to be permanent. You can have rising barriers. They can be manually operated or automatic. So again, for the older shopping malls on Orchard Road, in the bottom centre picture, they've fitted adaptable barriers, an automatic barrier in the top right from a building in the centre of Sheffield, and then Sheffield Meadowhall development on the left here, which has rising gates at the entry to all the external areas to protect it from flooding. Sacrificial areas don't only restrict themselves to pond areas in urban areas. We can have sacrificial floors to buildings. Ground floor, sacrificial ground floors. What other use could we use the ground floors of our buildings which weren't so vulnerable to flood water? So the concept of building on stilts, and in some areas, particularly where you have communities which have wooden homes, whole homes are propped up. I'm not suggesting that's necessarily going to win a design award on the bottom right. Indeed, I wouldn't necessarily apply a design award to any of those. They're just examples of a different way of thinking about how we design and manage our building stock to make them much more resilient to flooding. Floating homes in the Netherlands. The top picture is the classical picture many of you will have seen. The development you may not have seen, which is from Dordrecht, in the bottom picture, which I visited with some members of Parliament. That's the British Parliament, just to be clear. Last year, on a fact-finding tour as part of the EFRA Select Committee inquiry. And then designed by a colleague of mine who works for Backer Architects, their can float home. We started to call these can float homes on the River Thames, of which a number of these are now under construction, and this one in particular is now finished and operates. And this goes up and down with the water levels. It has a buoyancy tank in the basement and some vertical guide rails, and the home doesn't actually float. It sits on the ground normally, but under flood conditions it rises. And so it doesn't suffer like the Dutch homes where you put the grand piano. And then the buildings themselves, improving the resilience of receptors. Temporary flood barriers, great way of retrofitting, unlikely to keep all the water out, so we also need to look at what happens within the building. And the top left picture, you see a typical reinstatement of a flooding home, putting back all of those materials that are susceptible to flood water, instead of moving towards a much more sustainable approach where we start to use water-resilient materials and methods which help to manage water within buildings and stop buildings being out of action for many, many months after they are flooded. But what we find is when we start to address all of these issues from the source pathway receptor point of view, this different approach to managing flood risk, we suddenly find we open the doors to a whole load of other benefits. We find that when we start to store water at source, we can also provide features which improve the water quality, as in this development again in the Netherlands on the left, where we're using a little wetland to improve water quality, a rain garden from the Americas, retrofitted to a school on the right, and then the green roof from Malmö in Sweden, all improving the quality of the water that runs off from our areas. Scheme we've been delivering in Indianapolis, improving biodiversity as part of the flood risk management programme by using natural features. The amenity I mentioned earlier, the left-hand scheme from Malmö, was specifically designed with representatives from the local community, not just to manage flood risk, but to provide a nice place to live in. The right-hand picture shows where we now are with the Conswater Greenway project in providing a recreation facility for the people who live in that area of East Belfast. And finally, health and well-being. From Copenhagen, from Denmark, on the left, we've got this rather nice layout which uses water very much as a design feature to create this nice area in Frederiksberg. The top right-hand picture from the Netherlands, I'm not so sure we would necessarily go with some of the design detailing for the cycleway there, but nevertheless, it's a different cultural approach to water. And finally, in the bottom right-hand picture, we've got the Conswater Greenway project in its finished state. And Queen's University Belfast have done a research project which demonstrates that the value of the health benefits, the reduction to the cost of the health service from that community through having this opportunity of extra recreation, more than pays for the total capital cost of that scheme. So in conclusion, let me remind you that I don't think we can afford to defend against all flooding, and we need to be actually clear with society on what our ambition is there. What do we defend and what do we manage in relation to flood risk? Shifting our thinking from defence to resilience, limiting the flows entering our drainage systems, managing exceedance flows on the surface, and creating sacrificial storage areas. Making our receptors much more resilient to flood water, and perhaps above all, using those features to create a better place to live. Thank you.
Thank you, David. And our second speaker is Dr. Mark Wilkinson. Mark works at the James Hutton Institute, and his prime focus is on natural flood management.
Thank you, Sarah, and thank you for the invitation today to speak. I'm going to be trying to answer this question about how can we manage catchments to reduce flood risk. And I have to actually thank David for his talk there, because I'm going to show you some similarities about how we can manage water in rural catchments, similar to urban catchments. Introduction, like with the previous speakers, we're seeing quite a lot of floods recently, and highlighted here the aftermath of Storm Frank and the River Dee. And traditionally, we manage our flooding by traditional flood defences, flood walls, for example, like this one here in Keswick. But is this our future? Can we keep building flood walls higher? Now, I found this interesting image from the Danube, which kind of shows you we can't really keep building them higher. In fact, I would be quite scared to live in that house there. It's quite a worrying picture. We can keep building higher, but we need to look at a full range of measures. And the measures I'll be talking about today are natural-based approaches, but things like property-level protection, traditional. But we've looked at, Haley's given some examples about climate change. I want to quickly give an introduction and maybe about land use change and how our catchments have changed from the past. And this is Tarland in Aberdeenshire on the River Dee. And this is a map of it we found from 1832, and it shows it as a nice wetland system and lots of wiggly rivers and trees there and riparian planting. And then the agricultural revolution came along. Striking difference that we have basically canalised a lot of channels, we've created drainage, and what you don't see on there is we intensified our agriculture, and also we built on the floodplains, which is also a risk. But we move forward 100 years and nothing much has changed. We just bury a lot of our ditches. So it's quite striking, not much has changed there, maybe a few trees more, less in places. So I'm going to look at this from two aspects, really. I'm going to really spend a lot of time on this, what measures are at our disposal, how they work and where we place them, and look at, again, the integration and multiple benefits, which I think is important, and finally looking at communication, delivery and funding. Brief introduction to natural flood management. I'm not going to go into detail on this, but it's a catchment-based approach that works alongside traditional engineering approaches. And it's quite embedded in the policy, the Flood Risk Act of Scotland, 2009. And that places responsibility on several government bodies to cooperate to promote NFM techniques, which is great. It's a great piece of legislation. But it's trying to take that forward and get these projects off on the ground. I'll try and show some examples here. I want to put a statement in about many terminologies, and it can cause confusion because some colleagues from south of the border might know as working with natural processes. You go over into Europe, natural water retention measures have been used. You also see things like SUDs and rural SUDs, green engineering, natural engineering, the list goes on. This capsule phrase, which we've just recently worked on a paper on, nature-based solutions, is trying to bring this all together into one terminology, but lots of jargon there, and that's just on the definition of the subject itself. Look at specific measures. We can probably have a debate about how many terms there are for a leaky barrier, large woody debris, beaver dams, beaver lodges, it goes on. There's a lot of definitions out there. So I want to try and summarise that up. Firstly, looking at the types of measures at our disposal, woodland planting, land use management, better improvement of the soil in the uplands and lowlands, river restoration techniques, and coastal, but I won't talk much about that today. In fact, I'll focus mainly on land use management and river and floodplain restoration. But 4 words to sum this up, and in fact, I'll take it down to 1 word. Slow, store, filter, and disconnect, or just basically attenuation of runoff in the landscape. But how do we do this? Well, we need to take a catchment-wide adaptation to flooding, really. And like David, I like to take a management on a source, pathway, receptor approach, where our sources are really the land management itself, whether that be a farm, forest unit, the water on the landscape itself, the soil, the ditches, the small drains there. But floodwater will get to rivers, so we need to have better management of the rivers themselves, the pathways, allowing more room for the river in the appropriate places. But I'm not taking away the need for receptor management. That's key, and there's a place for that. So it's using all tools within our in our toolkit. I'm going to be looking at some local scale examples first. I'm going to use the River Dee as an example and try and use some data fresh off the press from the period of Storm Frank and afterwards to bring it in line with this meeting. I'm going to be looking at Tarland for source management and then upstream of Braemar for pathway management and linking that to multiple benefits. And the nice thing about these two catchments is Tarland's quite an intensive arable livestock area, whilst the bit upstream of Braemar's, Cairngorm National Park's picturesque Cairngorms, may not be as natural as you think when I show you some images. So firstly, this is one of my favourite images from Storm Frank because that's leading into the rivers. That is our sources generating lots of runoff. They're saturated, producing runoff, heading into to the streams or even into the towns themselves. And these tramways, they act as a sort of a micro pathway heading down. So we need to manage these better. So in Tarland in Aberdeenshire, we've been working with the McRoberts estate there, and we showed the concept using the GIS tool we've developed. And actually, that image maps nicely onto that left diagram there. And we proposed a way to store water coming off the field system, their 32-hectare field system, and stop it getting directly into the village. And I think we sometimes forget about that. It's not about just water going into the rivers, but actually it can go head straight into the towns themselves, the villages. There was a wetland there previously, but it was filling up with sediment. So what we did is we created a soil bund to disconnect most of the flow, store it, and the fine sediments to allow the wetland to do what it does best, have good biodiversity and nutrient reduction potential. And also looking at the soil management. I'm going to focus on the soil bund. There is engineering in that. We use the term natural, but actually it's more engineering, soft engineering in here, because it's got an engineered spillway. We don't want it to erode over the top. We want this to stay in. And it's got an outlet pipe to have control. And I'll show you why that's important now. Because actually, this is the Storm Frank period. First peak of Storm Frank. It's working remarkably well in Storm Frank. It fails, and it does what I really like it to do, be empty, in line with the previous talks, and David's talk, like an empty, full rain, but it's no use. We needed to drain away to have capacity for the following event. But the issue here came after the new year, as I like to call the storm with no name. Makes you think about naming of storms. And this is the storm that affected Inverurie, Port Elphiston, the Don, and Tarland itself. The ground's completely saturated, and the pond's full. It still has a bit of attenuation, but it's not performing as well as it should, showing that we need extra storage for these types of extreme events. I should mention the cost of this. I must thank the estate because they took the cost on themselves. They saw the potential of this for soil management alone just by collecting sediments in the field. But estimate of cost of that? Hundreds, really. It's a man with a JCB, really, sort of to come along and help to construct this. So, performance throughout the year. I think this is important to highlight, and going back to Hayley's point, we talk a lot about depth and duration, and sometimes we forget about intensity. So you can see it working quite nicely during the Storm Frank period at the beginning, and then it's full. And I've put soil moisture data from a nearby soil moisture site, but what is a soil moisture measurement we have there in the catchment? But what you can see is this intense rainfall event in June. The soil moisture is quite dry, and we see the pond filling. So we could assume that's infiltration excess overland flow. Basically, it can't infiltrate into the soil quick enough, and it's running off. And that's quite important to manage those types of events too. So we need to design, and this is working quite nicely for that event, to capture the runoff, but also the fine sediments. These can be highly eroding events. And again, highlighting sediment risk. So it's critical to understand the antecedent conditions, manage storm depth, duration, and intensity. But most importantly, I like to highlight is the farmer can still use this field. It's dry most of the time. So that's an important point to say. Source management during extreme events. I'm going to move to riparian buffer strips here and some work of my PhD student, Lindsay McLean. And, you know, what we're showing here is the performance of riparian buffer strips during many different events and highlighting extreme events here. But we assume riparian buffer strips just filter the runoff and act as sort of a roughening capacity. But actually what we saw in this riparian buffer strip is the micro-topography of the landscape, the plough furrow and the tram line, act as a conduit to send the water past the buffer strip to the corner of the field. And you can see photographs from the Storm Frank event. Well, actually, this was just after Storm Frank, on the 7th of January, sorry. And water's gone to the corner of the field. So I like to take a sort of a treatment train approach here. I would instantly think to put a bund in the corner of that field to collect water. So we can improve these to work better for flood management. I should mention there is, you can't see quite in the photograph there, the stream water is quite brown. It's carrying a lot of fine sediment. That's quite concerning. And one thing I'd like to highlight here is we're capturing overland flow, but a lot of water gets through subsurface drains in fields. So we need to manage this better. So one bit of work we're doing with my colleague Mark Stutter in Balready Farm, our research farm near Dundee, is creating eco-engineered buffer strips through this project BufferTech, working with the Danish. This is a valuable bit of land. The farmer uses 95% of the field, and we have this small little stretch of land, 10 metres wide. I've just highlighted in the last slide that it's not very effective. It has some reduction, roughening effect for runoff, but there's a lot we can do, more we can do. So what we've done here is we've broken the land drains into these storage ponds here, which can be drained down to allow to have capacity for the flood events. That allows the water to infiltrate through a bioreactive root zone of, say, willow. The farmer can use that as an energy crop, and it drains into the stream. So we're trying to maximize the multiple benefits of this important area. And this is 6 months after establishment, and you can see it's quite, like a normal buffer strip, but with some ponds in. And they help to break the subsurface flow and add storage during rain events. But just showing you some data here from last year from our nitrate sampling. The take-home message here is the nitrate is very high for this. That's quite a high concentration of nitrates. It's higher in the field drains, so that's that blue line there. And as it goes into the stream, it's lower. So there is a denitrifying effect going on here through most of the year. We should highlight is if we didn't break that up, that would have headed straight to the stream. So it's the importance of managing these subsurface flows. I'll move on now to pathway management and talk about how we can make more room for the river. Mark mentioned about the SEPA natural flood management maps. I think the floodplain maps are a great tool. They show great potential areas for floodplain storage. And actually in the Cairngorms, there's a lot of good storage on floodplains, which are doing a lot of good at the moment, but there's more that can be done. And I'm going to show you this example from the Mar-Lodge estate. It wasn't directly a flood risk management project. In fact, it's one of the multiple benefits. It was actually delivered by an integrated partnership approach, looking at other things such as biodiversity, geomorphology, and aesthetics. I'll come to that point later, because traditionally an embankment was put up here to protect the floodplain for agriculture. But as you can see here, the River Dee wants to head back to where it used to be, meandering through the floodplain. And in the 70s, it breached again. So the landowner at the time put a call out and asked for any material possible. About 35 to 45 old cars went in there. There was rumoured there was a tank in there as well, but I don't think they found a tank. But this was a lot of rubbish, and that was a problem for the Cairngorm National Park. This was a picturesque scenic route, and you could actually see these corrugated iron. And if you went closely, you could see an old tyre popping up. You have to watch out when you're at this field site. Health and safety was quite interesting. So post-restoration, it's been lowered. Then Storm Frank came along, and floodplain's doing what it should do lovely at this point, because there's no risk at this point to properties. And after, you can see actually it's lowered the flood embankment, but the river has been connecting more to the floodplain. The take-home message here is spot the difference. The river bar has now moved, and my colleague Steve Addy has been out surveying. So if we take that red line, this is a topographic cross-section. You can see the blue line there is before restoration, the embankment, and then the dotted line is a lowering of the embankment. And then post-Storm Frank, you can see it's eroded down a bit more. But the key thing is the incised nature of the channel has filled in, so the morphology is changing. Now, we need more data because we don't know if this is a natural process. It's the key thing about Chris made about we need longer data sets, the issues of natural variability. So, but you can see it's quite interesting that the geomorphology, and that's an important point, the role of geomorphology in flood risk management here as well. I just want to take home message, but I'll not say too much on that today. And here is not a very high flow event. This caused no flooding, but just showing you reconnection onto the floodplain there at this site, delivering multiple benefits, which the project set out. Pathway management during extreme events. Well, as scale increases, so too does the amount of storage you would need to require. So natural floodplain storage might not be enough. Certainly, southern England, we're quite limited with space of where we can store water. Certainly in parts of Scotland as well, we're quite limited. So we may need to further engineer our floodplains and offline storage areas, bunded areas on floodplains or washlands. But that makes us think, well, where does this fit on the scale of natural approaches to traditional engineering? Sometimes I have a problem with natural flood management because actually the true approach of natural is leave the system alone and let it get back to normal itself. If we plant trees, we engineer. But I'm talking here about offline storage washlands probably being this middle ground. And we talk about the concept of NFM plus, trying to add further storage capacity into the system. But is it one large reservoir? This is research we're trying to look at the moment. One large reservoir, we should be looking at lots of many smaller ponds. Well, you might think from a planning perspective, that's easy, the one large reservoir. It comes with lots of legislation, such as the Reservoirs Act. But lots of smaller ponds could deliver a lot more multiple benefits shown those previous slides. So local scale processes are fairly well understood, but further research is really needed at a catchment scale to understand these issues of clusters of measures. What is the role of each individual measure? Such as if you model a leaky barrier, well, the role of the leaky barrier is to send water onto the floodplain. So the roughness has a key issue there. And synchronization, where should we be doing this? We don't want to slow down a flood peak that actually needs to be released quicker within the subcatchment. So really our knowledge is known quite well at the local scale, but the interest, of course, is at this catchment scale. And that is a key thing we need to start to address further. To add more difficulties to this is NFM measures vary with their impacts in space and time. I'll not mention too much about woodlands, but the key thing is they take a long time to establish, so their impact will take time to establish. But they generally can be applied quite widely. Of course, the effectiveness depends on a lot of other factors. But things like leaky barriers are instantly effective. Well, in a way, they're trying to speed up the natural process of wood in rivers. We engineer these to slow down water. In the example here is a first-order channel in the Beaumont catchment on the Scotch borders. But the effect is spatially variable, even within the small stretch of river. So what you can actually see here is this is a survey of elevation change, i.e. the amount of sediment they're collecting and the effective storage. And you can see in the bottom graph, which is the period 1, there's a little tiny bit of net erosion of about a cubic meter, just as they settle in. But in the wet period, they're collecting a lot of sediment, and there's net deposition. So their effectiveness is changing all the time, the amount of storage. So there's lots of variation in this, and we've also looked at other types of structures in this recently published paper here. What we need is good catchment scale examples. We do have them in Scotland. I'll not say too much here because I noticed Chris has a poster, the Edelston catchment, where there are many measures and it's monitored catchment. So that will help us with our knowledge database. And also the Interreg Building with Nature project helps us to learn from European partners about their approaches and their ways of delivery. So my final point, communication, delivery and funding. Well, firstly, communication. Well, farming and land use varies from place to place, so do the views and measures. And as I've just highlighted here, in sort of intense agriculture and extreme events, you'll get these sorts of flow pathways. But the last thing we should do is shout at farmers and tell them what to do. I can say this because my parents are hill farmers, and I know they don't like being shouted at. It's the wrong way forward. We can learn a lot from farmers about and landowners and foresters about the processes. They know a lot about the landscape. I also think we need to be careful about who to blame during floods. And I don't think blaming the farmers, the Cumbrian farmers, for the flooding there was the right way forward. Probably should be blaming Mother Nature itself. And again, Monbiot with the science as well. We have lots of good science, but we need to be communicating this effectively to the right people in the right way. So I think this sort of statement about the blame game and the communication of evidence we need to do carefully. Work such as the Tweed Forum about communicating through catchment models, I think is great, and just getting this two-way conversation going, or multi-way conversation going between partners. One way we've done this with a tool I developed with partners at Newcastle University when I was down there, is the farm tool. And basically it's a matrix that tries to communicate the risk of runoff into those two categories I talked about in my earlier slides, the soil infiltration and tillage regime and flow connectivity as the two factors that control flooding in a field. You could say soil is a factor here, but we do it on a field-by-field basis to keep it more simplistic for the communication. And here's how it plots. So your risk would be quite high if your soil's in poor condition and highly connected to the ditches. And the top one shows if you have good soil structure and wetlands disconnecting flow, then you're in the lower risk. But I certainly know we like to say that if you're down at this far bottom end, you're probably not farming. And this is the issue that I'll now move on to, is about what do we want from our landscapes? We still need to make food in them. And how do we ensure measures stay in for the long term? This is one of the first sites myself and Paul Quinn at Newcastle University started work with on this farm. And again, slides from linking to earlier slides, field runoff, what can we do? Corner of field pond, collecting a lot of fine sediment. So we built this. This was an experiment. There's no flood risk. It was just trying to learn about the performance of these features. And it's working nicely through time. 2009, the project ended, and the land manager was just left to take it on board to his needs. And it was removed. Now, the reason why I highlight this is soil buns can be removed. Woodlands can be removed. Embankments can be put back in. So therefore, you need to make sure that after the project's finished, there is new funding for maintenance and management, and partnerships are there to advise people when things go wrong. So we need to always make sure we're in this for the long run. And catchment partnerships are key to that. So I think we need to think beyond political cycles and be aspirational. I say that generational cycles, we don't know what's going to be happening politically in the next 10 years. So this is a challenge, really, but this is where we need to be going. And we should be thinking about flood risk solely, and I agree with David. We should be looking about the full integrated catchment approach, looking at the multiple benefits and asking questions about what do we want from our catchment, learning from exercises such as the land use strategy pilot. And the statement at the bottom really also strikes home about in the Lake District, the National Trust trying to do good work for natural flood management there, but they get criticised for buying land and planting trees there because people want to see the landscape as Wordsworth did. So do we now expect our landscapes to be bare? That's what we've grown up with. What do we view from our landscapes? This is an interesting one and debates we need to have. So final thoughts, take a catchment-based approach. It's all looking at the sources themselves, the fields, the forest, down to the pathways, the rivers, and not forgetting this is not trying to take away from traditional defences. It's the full suite. The approaches may have varying impacts in space and time, as I've just demonstrated. But just going to Hayley's point about climate change, well, climate change carries a lot of uncertainty, but we know it's pointing us in the direction of change. Well, natural flood management is probably in a similar way. It has a lot of uncertainty at the catchment scale, but generally the uncertainty bounds are pointing us in the direction of it's doing good. And therefore, that's why we need to really ensure, we take this catchment-based approach. Just basically, even if we sold it on the multiple benefits alone, what the ecosystem services can provide. So I like to see it as a climate change resilience measure, maybe, climate proofing, even if it did add a centimetre or two, maybe off a flood peak. But, this is why we need to work more and gather this evidence. And delivery, catchment partnerships are key, but it must include the landowners, they're valuable, and the communities themselves. And I'm quite inspired to see communities themselves taking natural flood management forward and understanding what its limitations are and what it can do. And I'm quite inspired to see communities such as Stonehaven and recently at the Sniffer Conference, the Falkland Flood Group as well, doing natural flood management themselves. But we just need to ensure that we get good, the evidence as it comes along to them directly to help with the planning and long-term maintenance of these. I'd like to thank my co-authors and a few acknowledgements there, and I'll stop and take any questions.
Thank you, Mark. Yes, we've now got about 10 minutes for questions, and again, there are people with microphones, so if you can put your hand up if you've got a question.
Thanks to both the speakers, some very interesting talks. It's Tom Ball from University of Winchester, actually, not Dundee, as for the programme, used to be at Dundee. A cross-cutting theme for both talks, so I think I can address it to both speakers, is the importance of something being empty. I think that came out from both the water, the B word I'll use, water butts I think is fair enough, but if they're empty. But I think it also came into Mark's talk, quite interesting there, with the Tarn feature and the other features that you pointed out from your previous work. Now, I suppose the question is there a trade-off between, particularly from the natural flood management perspective, Mark, the multiple benefits aspect of this and the engineering hydrology aspects? Because it strikes me that where we have the importance, as you pointed out, of the feature draining out between events, so making sure that it is empty and doing its work, but also an empty feature not having those kind of wetland multiple benefits, the sort of things that the catchment stakeholders might buy into more. And I'm just interested in, I think from Irva's perspective, also David's view on this, whether there is a need to sort of find a happy medium here. And I think your double-ended arrow there at the end of your talk, Mark, summarised that well, of whether we have a kind of engineering versus natural trade-off and where we need to kind of fit in our hydrological work within that continuum.
Yes, very good point. In the Belford project, we tried to create a sole feature that delivered as many multiple benefits as possible to please all the stakeholders. It's very difficult. It's a very good point, because of course, I'm interested from a flood perspective, and like David, an empty feature is a good feature for flooding because it has further attenuation. But an empty feature from an ecological perspective is not very good. So like a wetland needs a wet area. So I like to look at this more as a treatment train, whereby you build a measure that's got capacity to, say, a wetland which has some water storage. And you can do that in very close proximity. In the way the buffer tech project I showed you is just a treatment train in a very compact space, but you could actually make it on a larger scale if you wish. But yeah, I think we do. You need to have connection of measures and trade-offs.
I suppose being an engineer, I'm going to approach this from the engineering hydrology point of view. So, and I just think back to a scheme I've been working over the last few weeks, talking to the team about being clear about what the catchment faces at the moment. What are the flows that are generated from the catchment at the moment? And then looking at where do we need to be? How much do we need to reduce those peak flows to get to an acceptable level of performance? And from a very simple attenuation point of view, how much storage do we now have to incorporate in this catchment in order to achieve that? So having got that figure, we've then got over here, we've got the toolbox. So we can now start selecting things from the toolbox, and each of those can do different things and be appropriate in some areas and not appropriate in other areas. But if we can't, with the range of measures we're pulling out of the toolbox, generate that amount of storage volume, we're not going to deliver the amount of attenuation which we need. And I'm very excited about all the multiple things we can do with these measures, as I've mentioned in the presentation, and I think was nicely demonstrated in the last presentations. But what I don't want to do, what would be a tragedy, I think, here, is misleading people about what can be achieved with these different measures, simply because we just don't get some of the basic numbers right.
Yeah, just adding onto that one, I would say, although we talk about multiple benefits, you don't have to try and achieve all the benefits from one measure. So you can have a range of measures to achieve a range of benefits, but also some of the examples that David was giving about storage areas in an urban context where you're quite happy that they're dry most of the time, and that's a kind of recreational space, and then it's then used for storage in a flood event. So it's thinking about the range of different measures you can use and the purpose you want them to fulfill. Right. Any other questions? Lady at the back there.
Hi, my name is Emer Owens from EnviroCentre. David, you directly referenced some difficulties in sort of municipal planning policies and approaches, and certainly your slide showed a huge difference across countries of how open they were to innovation on flood resilience. And I'm sure, Mark, that you've come across similar. In your opinion, whose responsibility is it to start lobbying a changing approach to innovative engineering and innovative techniques for flood resilience? Say is it the likes of professional engineers, hydrologists, statutory bodies, or even, you know, due to your involvement with ICE, professional bodies such as themselves? Because I think the industry is in danger of perhaps implementing what's allowable by policy rather than being innovative, and especially that's due to a client has only so much budget, so you go exactly as per what's policy, and they don't want to risk being innovative and going down the wrong path if it just gets rejected.
Well, we could have quite a lot of discussion around what fosters innovation and what are the barriers, but we won't do that. Let me just say a couple of things. A little while ago, I did a study of international best practice in this area on behalf of Ofwat, which is the water company regulator in England. And they wanted to learn more about this exact point that you're making. Who's responsible? Does the organisational structure make a difference to what fosters the delivery of some of these more innovative methods? And what I found to that question, the answer to that question was no. You listed a whole range of different potentially responsible bodies there, and said, you know, who should lead on this, and which one of these should, and I would say, yeah, all of them potentially. But what actually is most important is having a local champion. It's somebody from one of those organisations who has the vision to do something differently. So that's the first thing. The second thing, of course, that needs to happen then is that person has to be, you know, properly supported. But I think one of the dangers we have is when we come up with a new way of doing something, we all sit down and we put all our energy into working out all the different things that are going to get in the way of that working, why it won't work. And that's the main reason, in my view, why things don't happen. If we put that energy into answering the question, what would it take to make this work? So, you know, if you've got a champion in place and they've come up with an idea which they're passionate about, what you focus on working on is, what would it take now to make this work? And you work slowly with all the different parties, and sometimes it does take time. But I would really encourage those of you who have a mind to go down some of these new pathways to do exactly that, because you will get there in the end. It is difficult and it's hard work, and sometimes it's difficult to see change, because change is difficult to see on a day-to-day basis. But at the end, you'll turn around and you'll look back over that period of time and you'll think, wow, we really did it.
Yeah, very good point. And just to follow up on that, I fully agree with that. And it's not really a linear scale in terms of time needed. We found in Belford, actually, the natural flood management scheme there, it was the first feature that took so long, because you had to get everyone together, understand everyone's needs, what you need to do, this aspect, that aspect. And even the farmer just shown, you know, listen to an example, his opinion. But when everyone sees it working correctly, and you get that little bit of evidence, then you start to rocket off and deliver a lot more things. But it's usually at the beginning that's the slow bit. Generally, it can change case by case.
Okay, I think we've probably got time for one more question, the first one. Ooh. Well, okay, I've got one final question for you, Mark, then, is what do you think we need to do next in Scotland in relation to taking forward implementation of natural flood management?
I think there's a few things, but the key one is two aspects. First one would be integration, and try work closely with our partners in, say, diffuse pollution. As I've just highlighted, there's a lot of measures there, diffuse pollution measures, which have a natural flood management benefit, and they could be optimized to have flood storage. So I think that's a key aspect. Secondly, I would probably say is there's lots of good legislation there, there's lots of good top-down tools, but we just need to encourage the bottom-up way of thinking as well. These community groups give the support there, give the knowledge. But I think we're in a good position sort of from a policy top-down level. It's sort of, we have lots of natural flood management plans being developed by the local authorities at the moment, but how do we implement them? How do we convince the landowners or have that dialogue? So I think it's getting that next step correct. So we've got the sort of plans and the knowledge. It's now how do we implement it?
And it's the same in the urban context. It's exactly the same.
Right. Okay. Thank you. So I'll be handing over now to Professor Roger Crofts to chair the next session. But before I do, could you just thank the speakers, please?
People escaping. Freedom.
I thought there was a mad rush for the door then, but don't take it personally. The next three speakers, I'm Roger Crofts, Chair of the Royal Scottish Geographical Society. We published our magazine, The Geographer, and an issue on flooding in autumn 2014. If you haven't seen it, go on our website. And I think we are going to try and persuade all the speakers to submit their papers and publish them in the Scottish Geographical Journal, because it's ideal. I'm biased, of course, but geography is the bit that connects all the pieces, and therefore is the subject of our time. Anyway, that's the end of the slogan. We're now moving on to dealing with the impacts of flooding. And we've got three speakers, and I'm delighted to welcome first Michael Cranston, who is an honorary research fellow at Dundee University and has recently set up the Scottish office of RAB Consulting. 10 years of flood warning developments in Scotland. What opportunities remain? Over to you.
Thank you very much, Roger. Okay, good afternoon, everybody. Thank you, Alan, and the committee for the wonderful opportunity to speak and present, and great to see so many colleagues that I've worked with over the many 10 years and beyond. What I'd like to cover today is in 4 parts. I actually want to step back to before the Act, which has been referred to several times today, and the Flooding and Flood Risk Management Inquiry, which, show of hands, who gave evidence in that inquiry 10 years ago? There should be more than one. Come on. 2. There should be more than that. I know a few people. When I've read it in the last few weeks, there's a few familiar names there. So I want to touch back to the inquiry, because noting Alan's driver for today is looking to where the challenges are, where the future opportunities are. We had similar questions back in 2007 and 8. So actually, what have we achieved in the intervening 10 years? What's changed? Have we improved flood warning? Then I want to touch upon a research project I'm involved with at the University of Dundee on assessing the effectiveness of Scotland's public flood warning service, which is, thanks to SEPA, it's very close to concluding. They gave us permission to present some of the findings today, which is excellent. And then just 2 slides at the end on what I consider, and shared these views with a few people that I've got respect for, in terms of future opportunities in flood warning. I'm going to start with my acknowledgements. I'd like to thank David, Pascal, Cordelia and Louise from SEPA for comments on an earlier draft of this, which meant I had to get the slides done 2 weeks ago, which was great. And then colleagues at Dundee University, Alice, give me a wave, thank you, who's our research assistant on this project. Any awkward questions, Alice, be lined up for them. Andrew, Alistair and Alan, who's on the project team as well. And then just 2 references at the end, Crew, who's funded this research work, and something right at the end, we've got an incubator grant funding from Checker, which I'm going to refer to as well, and the future challenges. Okay, Flooding and Flood Risk Management Inquiry, which started about 10 years ago, reported in 2008. There's a lot of talk this morning about flood-rich periods. This inquiry clearly was formed on the back of a flood-rich period. I've got a few interesting floods, starting in with Strathclyde, 1994. There's been a few images of that today, and Glasgow, 2002. Elgin, 97 and 2002. Hoyk in 2005, which I'll refer to, and Stirling in 2005 and 6. So really on the back of some significant flood events, and you can see 2 images there. Now this drove obviously a lot of thinking around how we can improve flood risk management in Scotland, which ultimately led to a more sustainable approach through the Flood Risk Management Scotland Act, which you've heard about. So what I want to do is reflect on the flood warning aspects of that inquiry, look back at some of the recommendations that were made, and reflect on what they achieved and how far we've come in the years since. So, see some quotes there from the inquiry. The key for flood warning was around the continual development of the warning service, and in addition suggesting greater emphasis on effective warnings, and I'll talk about that in detail. And there's an interesting quote from ACPOS, the Chief Police Officers of Scotland. They were involved, and I was talking to Richard Brown earlier, in terms of their role in flood warning from the 80s and 90s, where they had a role in the cascade systems in many catchments. And they said public expectations around flood warning systems can never fully be met. So obviously that is a big challenge, and they were speaking from experience. So I'll go through that in terms of have these challenges been met through the flood warning service over the years. One of the first recommendations was around giving SEPA the ability to disseminate flood warnings to end users. At the time, warning dissemination systems were sporadic. There were different arrangements in different locations. Some local authorities had taken on the responsibility, like Scottish Borders Council. The police were making noises to move away from cascade arrangements because of the introduction of the floodline call centre, which came into operation in 2001. So on the back of funding from the Scottish Government, SEPA introduced an active dissemination system of flood alerts and warnings, which after 3 years of development went live in March 2011. A large programme to develop a multimedia system to disseminate warnings to anybody who wanted to register, free service. And that service has grown significantly over the years. There's now 26,000 customers. The last I heard anyway, it's probably gone up since, given that it is growing on a regular basis. So that's been a big change, and I'll reflect on the public research that we've done around the effectiveness of this public service. Another recommendation was around upgrading flood warning systems and expanding to uncovered areas. The development of flood warning, as likes of Richard and Nigel would know because they've been involved in it, was largely on the back of major flood events in local areas, the Tay scheme, the Highland scheme. These were developed by local need. There was never a really national approach to this. So starting with the new schemes in the southwest, the Clyde, Kelvin and Irvine, and the new schemes in the northeast of Scotland in 2010, SEPA published the flood warning strategy in 2012, and it was the first opportunity to really take a prioritised approach and a national approach to the development of flood warning. That's a picture of the floodline customers and registrations as of 2012. And one of the aims was to obviously increase the coverage and look to, as Mark mentioned earlier about potentially vulnerable areas, to aim to achieve flood warning to 65% of these areas by 2016. Now this coverage is obviously expanding further. There's plans to launch the Cree, Loch Lomond and Garnock schemes imminently, and then SEPA recently published the new framework for flood warning as well, which looks to the next 4 years of further expansion. One of the biggest challenges around flood warning, as anybody's been involved in this area, and it still remains one of the biggest challenges, is surface water alerting. One of the recommendations in 2008 was around filling the void that exists with regard to pluvial warnings. Now, back in 2013, we had funding through CREW to get the lead scientists together through CEH with the grid-to-grid capabilities and the Met Office through their high-resolution precipitation models to look at how, in terms of the science, we could develop a forecasting capability to underpin surface water alerting. Now, the driver was for Glasgow, given the Commonwealth Games in 2014. You've seen images of Glasgow in the big 2002 surface water event, and the idea was, could we develop a system to give the responders, emergency planners during that event and the games organisers a heads up 24 hours in advance of potential for flooding. Because if you've got any games activities going through potentially flooded areas, clearly that will be an issue for them. Out of the science came a pilot of a surface water alerting capability. If you want to read the full report, it's on the crew.ac.uk website. And it was a real novel approach combining ensemble rainfall forecasts to the grid-to-grid model, looking at surface water runoff, and then linking to an impact library of impacts, people and property, transport, railways, roads, as you've seen earlier about the road pictures, in terms of flooding in 2002. So it's quite a novel approach, and it was the first UK operational surface water flood risk forecast. I mean, the capabilities, as Nick alluded to, has developed further since. But it did really answer the question of filling that void that was proposed back in 2008. One of the other recommendations is around collaboration between the Met services and the hydrological services, providing effective warnings for all types of flooding. So building on what I've said around the surface water capabilities, back in 2011, the Scottish Flood Forecasting Service was established, issuing the flood guidance statement. That went live in 2011. How many people, again, hands up, sorry, activity afternoon, who receives the flood guidance statement? What would we do without it now, if you think about it? It's incredible, the step change in what that's delivered in the early heads up. And I encourage you, if you've not seen it, go and see the poster paper by SEPA in terms of the early warnings and the communication, the build up to Storm Frank, in terms of having that 5-day forecasting capability. It's a real step change. In terms of underpinning that, the science capabilities about linking high resolution weather models. Hayley mentioned the UKV model, also MOGREPS, which is now coupled with countrywide flood forecasting capabilities using grid to grid. And that's an example of Storm Bertha, where you can see output from grid to grid, linked to forecasts at a gauging station, and then that's the area of concern map that was produced on the back of that. Coastal warning systems is obviously a key gap back in 2007 and 8. There was only the Firth of Clyde flood warning and forecasting capabilities in operation. And the recommendations clearly followed the fatalities that we had, unfortunately, with the West Nile storm in 2005, which then led to the introduction of the Storm Tide Forecasting Service. Now, since then, there's been a lot more focused attention on developing forecasting capabilities, particularly around wave forecasting and wave overtopping. Mark mentioned it earlier in terms of the gap there. It started in 2002 with the Firth of Forth scheme, which introduced wave forecasting and overtopping for the first time. Clearly a big issue for us. These capabilities have now been introduced in a number of locations and will continue to do so. So just to conclude, I'm going to finish on this slide, which I've used quite a bit before, and I mentioned 2005. You probably all remember the build-up to the 2014 weather bomb. This is put across the media quite a lot. There's probably a lot of fatigue about the messaging going out about the weather bomb, but actually, were we better prepared about it? Science capabilities led to early forecasting of that, and that's the flood guidance statement for that event. And if you compare it to the tragic fatalities from 2005, what impacts did we experience in 2014? There was power loss. We can live with that. I think we were all better prepared. I think the messages led to a response which mitigated flooding, which I think is a good thing in terms of the capabilities that have changed. Okay, so 2015-16, the storms. That was clearly a big challenge to everybody in terms of the response. Those providing the flood warning service, it was a big test of the systems that had been introduced, a big test of the people behind the systems and the messaging. And following this, SEPA through Crew commissioned a study to look at how effective were the warnings that we provided. A couple of interesting stats, or one interesting stat, 300,000 messages went out during those months through the Public Flood Warning Service. So how effective was that in generating a response? What actions were taken on the ground? Who responded to them? Were the messages timely? Were they acted upon? These are all of the questions that we've been asking over the last few months through this research project. Our approach was to develop a web-based questionnaire which went out to all the floodline customers that we had emails for, which wasn't all of them, unfortunately, but it was about 19,000 customers. We had a very good response. 1,300, over 1,300 responded and have provided some excellent feedback, comments. The survey was designed for the first time to really test where the customer was, the location, the risk, the type of warning that they received, previous experience of flooding, different demographics, just to really test how different customer groups are using the service. And we've also carried out a number of workshops which have been fascinating, just to explore some of these some of the feedback that we've had in a bit more detail with customer groups. This is a picture from Nethy Bridge back in January. It was a fascinating evening in Aviemore, actually. I'll mention this one. There's a chap that came along, really interesting chap. Unfortunately, he's been flooded many times in Aviemore. I think it's the first property flood. He's been there 40 years. And he said, don't need SEPA to tell me when it's going to flood. I know when it's going to flood. And the guy came out with a notepad of all the records that I've got from his back garden to his house of every event that's occurred there. I mean, that's fantastic knowledge and should be captured. And hopefully we will capture it during the event. So really interesting comments we've had back during the process, which has been wonderful. We've taken the responses and obviously split them into different categories. We've geocoded them to make sure we know where the customer is, so we can then do further analysis on the type of warning they get, where they are, the risk. You can see here some of the statistics in terms of from the different message types, so alert, warning, or both alerts and warning customers. The percentage of those who've received messages in the past, which is a high number, and then the percentage of those who've previously been flooded, so we can understand experience and how that affects your response. And that's just a map of the distribution of, it's not a clear map, but gives you an idea of those who've responded to the survey. What we've also done as well is to try and categorise the warnings. And this is going into a little bit of detail, but we're keen to understand, does response to warnings, is it influenced by the frequency of warnings? So how many warnings do you get? Does that affect how you respond to it? And then the potential impact. So a simple plot here, if I'm a landowner, I've got livestock, which the warnings probably go out more frequently than other warnings, do I respond differently to say I'm a property owner on the slit rig in Hoyk, which only goes out very rarely, but when it does go out, it's quite a high impact. And you can see the 9 categories you've got here. Apologies if it's not very clear. But these are categories in terms of the frequency, so low, medium, high, and then the impacts, low, medium, high again. Quite pleasing to see we've had a very good spread, and it matches the SEPA customers quite well. So the lighter blue is the percentage of SEPA customers per category, and then the purple and the red are the survey responses that we've had. So we've got a good spread across the different customer types. So how satisfied are floodline customers? Just a couple of interesting pieces coming out here. Like I said at the start of the talk, we haven't finished the project yet. We're due to finish in the next couple of weeks. So these are really headlines coming off the analysis that we've done. So of those who responded, a high proportion are satisfied, 66% overall satisfaction. Interesting there that satisfaction does not depend on previous experience of flooding. There's no significance between the two. And then satisfaction is slightly higher with those who receive both types of messages, so both alerts and warnings, rather than purely just the alert or the warning message. So, simple comment. We've had lots of comments, which are great to capture and feedback. Keep them coming. Much appreciated. When I mentioned we've split the different types of flood warning areas into 9 different customer groups, or flood warning classification, this is an interesting plot that we discovered a couple of weeks ago. And you can see on the left of the graph, blue is customers who are highly satisfied, and red is those who are more neutral or unsatisfied with the service. So on the right are the ones, the warning areas that have been issued a high number of times. You're probably looking at, I think how we've classified this, greater than 8 times or 9 times. So those who get messages on a regular basis tend to be highly satisfied with the service. But actually, if you look to the right, the lower frequency, there's more of a less satisfaction with the overall service. And that was an interesting one for us when we saw that. Thank you. What about locally specific information? Through the workshops, people do get the principle of a stage flood warning service, so messages going out when it's possible, likely, significant. A couple of interesting ones here. 57% of those who receive only the regional alert messages believe it's a service for locally specific warnings. So these are messages going out for whole regional areas, when actually they think that service should be about locally specific warnings. So they're not really understanding that element of the service, unfortunately. And then 74% of these alert-only customers who said the messages were too frequent also said that the impacts were not as bad as conveyed. So there's an element there of potentially with the alert component, crying wolf, too frequent, not being locally specific to the individuals. What actions do people take? I'll go back to the cars shortly, but 71% who said they had property level protection measures deployed them when they received flood warnings. 62% of landowners who said they had livestock moved the livestock. So there's a big response in terms of the warnings going out and leading to actions. 42% of all responders said they removed vehicles on the receipt of a warning. Now, it's an interesting anecdote from the emergency planner from Scottish Borders Council. 2005, when Hoyk was flooded, there's a picture of the high street with cars being washed down the high street. And he said on the back of Storm Desmond, they happened to notice that not one single car was flooded in Hoyk. I think that's an interesting one in terms of the early preparation and planning that led up to that event. So some early conclusions. Customers of the Floodline Public Flood Warning Service are largely content. Least content, the least content customers are those who do not receive regular messages and are less likely to be engaged with the overall service because they're not really hearing about it. Flood warnings do lead to actions to mitigate flooding, as I included in the last slide. However, the regional flood alerts are probably less likely to lead to actions, given the lack of locally specific information, but also typically misunderstood about the role of the flood alerts. And for those who are well engaged, through the workshop, there's clearly an appetite for further access to river level information, even flood forecasting information. The amount of people that use the river level sites that SEPA have, the chap in Aviemore, okay, he doesn't receive the flood warnings, but he does go to the river level site. That's quite key. There's a high level of use of that. But there is an appetite for further information. We did present a couple of messages from a duty officer in Dingwall, which referenced forecasts. And the group said, well, that'd be wonderful if we could receive that. So there's an interest there for further information and to help them respond. So last two slides. Got time for this? Thank you, Roger. What opportunities remain for flood warning? I structured this around two, one around science and one around communication of warnings. The science, and I go back to the inquiry again. And where's Jim? Thank you, Jim. Jim will know about this because he probably has to handle the Scottish Parliament inquiries about having high-resolution radar for the whole of the country. How many times has that question come up? Half a dozen, yeah. Now, SEPA, Met Office and NCAS were involved in a trial of an X-band radar up in the Moray coastline. Lovely piece of kit, and that's an example of the output there. But actually, is it about, which wouldn't be feasible in terms of cost benefit, in terms of covering the whole of Scotland in C-band radars, is it more about using the information that we've got in providing better precipitation estimates? And there's a couple of initiatives underway at the moment about merging radar and rain gauges. So using SEPA network of rain gauges to then improve the radar coverage where there may be issues with overshooting of the rainfall, etc., and areas like the Moray coastline, which is quite poor for radar coverage. But also improve radar orographic scheme as well. I'm pleased to see Marjorie in the audience. She did a bit of work in the 80s, early 90s, particularly around this. And it's fair to say that I don't think we've really got there in terms of the orographic scheme yet. So I know there's a piece of work underway to look at that scheme again. In terms of modelling, looking back to what was achieved through the Glasgow surface water pilot, can we start looking at similar uses of the MOGREPS UK model, high resolution ensemble model, to then better predict, particularly for flash flooding and flashy catchments like Comrie, Stonehaven. This is a plot on the left here from CEH and also work from Clive Pearce at the Met Office. The blue, this is from the flood in 2002. The blue is the hydrograph, the observed hydrograph for the Erne, or the Ruckle water, sorry. The red was the forecast that we had at the time. Now the green was a pilot of using actually steps, high-resolution ensemble predictions into the grid-to-grid model. And you can see here the green plot suggests that this higher resolution model gives us a better chance of predicting these type of events on a short-term forecasting basis. Then around flood warnings, learning from the surface water trial, what we're doing with a small piece of work with Checker, we're looking at how we can communicate surface water alerting when there's so much uncertainty. When there's so much uncertainty, how could you encourage somebody to take action in terms of moving cars or installing property level protection? And what we're looking at here is just to test a few different methods, building on the risk matrix that are now commonly used with the flood guidance statement and the National Severe Weather Warning Service, but actually stripping it out and saying, well, okay, what's the risk to people, property, transport, in the same way that we did that with the Commonwealth Games trial, but actually can you do it to make it more focused on different impacts and different receptors? So there's an initial workshop planned in April, and we hope to come back with some early findings from that to think about whether there are new ways of communicating risk. Okay, I think that's it. Thank you very much for your time.
Thank you very much indeed. Those of us that live in flood risk areas ought to be really reassured by this amazing attention to detail, but also listening to what us, the customers, want to get from these flood warning systems. We now move to that really important question of flooding insurance. And it's a delight to welcome Edmund Penning-Rousell, who's been working on this, I think, for many decades, should we say.
Still haven't solved the problem, Roger.
Well, how do you solve the problem of the insurance industry? But I'm sure you're going to tell us something about that, what its limitations are, and the importance that it has to all of us. Edmund, over to you.
Thank you very much, Roger. It's a pleasure to be here at the RSC to talk about flood insurance in this really useful and exciting meeting. So I'm going to talk about the nature of flood insurance and when it's not viable, how we in the UK stand up to those criteria of viability in an international context. I'm going to talk about the situation in Scotland and analyse who gains and who loses. I'll touch on the situation, the new Flood Re proposal, which went live in spring 2016, and draw some conclusions. Now, one of the problems with insurance generally is that there are certain conditions that have to be met to make sure it's viable and for the companies to remain solvent. It must be possible to estimate the likelihood of loss. If you can't estimate the likely loss, you can't run an insurance portfolio. Losses from individual properties should be independent and random, and no single event should affect a large proportion of the properties affected, properties insured. In addition, the occurrence of a loss should be fortuitous, not capable of being predicted specifically. You shouldn't be able to predict specifically there's going to be an event tomorrow or the day after. Otherwise, people will only insure for tomorrow, not on a continuing basis. And, of course, the size of the premium should be acceptable to the insured, otherwise they weren't paid. And that's from Nigel Arnell's paper, which you can read. The problem with flood insurance is that it fails the second criterion. That is to say, you do get very large flood events where all properties which are insured in that event claim simultaneously. And when you get that situation, the company involved can become insolvent. And that's not really what you want to have happen. So we have a problem here, ab initio, with flood insurance. And, as I say, it fails for big events. And the major events can destabilize the insurance arrangements by making the companies insolvent. So we have to be careful. And you do get big events. Here's Desmond. You do get events that affect thousands and thousands of properties, as we have in Scotland and as we have had in England, particularly in 2007. And in the USA, they've had major flood events which have crippled the National Flood Insurance Program. This graph shows the debt of that program to the US Treasury, from which it has to borrow funds to pay for compensation claims. And it's now standing in excess of 30 billion US dollars. So organizations like this can become unviable. So we have to watch out. Secondly, how do we stand in an international context? And we've done some research on the robustness of insurance regimes worldwide. And what we've looked at is 32 insurance regimes evaluated for their robustness, that is to say their solvency, their technical solvency to climate change, looking across the world. And it's amazing what variety there is across the world. So, for example, in France, you have a system whereby flood insurance is compulsory because it's added on to your compulsory fire insurance. A very simple, mandatory arrangement. 100% penetration rates, as we call it. In other countries like Italy, you have less than 5% penetration rates because it's offered as an option onto other disaster insurance arrangements. And the option is not taken up by people who don't think they're at risk. And therefore, disasters, as it says here, are often covered by emergency taxes, which is really the last resort of a scoundrel in this particular area. In UK, we have about 95% penetration. If you know about your flood insurance, you'll know that it's bundled in with other insurance for your property, like fire, theft, subsidence, burglary, all those other perils that you might face. And you cannot separate out the flood insurance component of your insurance policy. That's a good thing in some respects, but of course a bad thing in other respects if you don't have a flood risk to insure against. What are our conclusions? Our conclusion is that the solvency of insurance arrangements in the UK are particularly strong. We have a very, very powerful, very strong insurance industry. Changing risk may threaten solvency if increasing risk, as we've heard today, is not recognized and adjusted for. But the best robust insurance policies are those which are based on some sort of market system whereby premiums can adjust to the kind of risk changes that we might face in the future. You may not like to have your insurance covered by a market private system, but it's actually robust in technical terms and hinders the process, reduces the process whereby insolvency might grow. And you can read that paper if you wish. Now, what about the situation in Scotland? I've been involved in a Joseph Rowntree Foundation sponsored project to look at flood risk across the country, building on the climate change risk assessment done last year. And here we have a map of the number of people exposed to frequent flooding up and down the country. And it's adjusted so we only concentrate on the areas which are particularly flood vulnerable, the particularly vulnerable communities in terms of their socioeconomic characteristics. And there's your map of the number of people that are affected. In terms of annual average damage, a long-term average there of these communities, we see that Scotland has its particular problems in the central belt, where there is flood damage occurring and has the future of continuing that damage in future floods. So that's more or less in balance with the number of people exposed. But what we also did is we looked at what we call the pain element of this, which is relating the damage you might incur in future floods to your economic circumstances at a household level, mitigated by the amount of insurance you might have taken out. So if you've got low damage and you've got insurance, your pain threshold is low. If you've got lots of potential damage and you're economically rather deprived and you have no insurance, the pain value is high. So what we see here is that Scotland has a particular problem which is not matched elsewhere, of a high pain threshold, a high pain level in terms of its susceptibility to damage which cannot be recouped by insurance cover. Now, that is added to by the fact that our analysis shows that the annual average potential damage per individual, taking individuals from these different census districts, is actually higher in Scotland than the other three countries. So the potential for damage is higher in Scotland, and I'm afraid your insurance penetration levels are lower. Now, here is a diagram which shows the insurance penetration levels, the amount of insurance taken out by the population as a whole in the rest of the UK and Scotland. And these levels of no insurance at all of those particular households, no insurance. It's 21%, 21.8% in the rest of the UK, but it's more in Scotland. You have less insurance in Scotland proportionally than you have in the rest of the UK. That's unsatisfactory. Why is that the case? It's partly because you have very high levels, as we do in the rest of the UK, of the lack of structural insurance for the property, the building of the property, whereas the contents insurance is broadly balanced. That's partly because the contents are covered by an insurance policy taken out by the householder, whereas the structure is a policy which can have to be taken out by the landlord or local authority. The situation doesn't get any better when you look at income deciles. So the poorest 10% by income decile are on the left-hand side, the richest on the right-hand side. And what we see then is that somewhere around 50, 54, 55% of people in the poorest 10% decile do not have any insurance at all. They are susceptible to the kind of damage that we see in poor communities from floods in the past and will see in the future. If you look across the different types of tenure, the situation gets worse again. So here we have the tenure of the property, the one circled here as housing associations. We're also looking at private tenants. We're looking at locally authority property as well. The numbers are relatively small, but the total sample, this is from the ONS Living Costs and Food Survey, is high at over 5,000. And what we see is that all tenanted accommodation has far lowest amount of insurance when compared with the owner-occupiers. And in every case, it's worse in Scotland than it is in the rest of the UK. Now, there's no real difference between the tenure breakdown in Scotland, between that and the rest of the UK. There is more private rented accommodation in the rest of the UK than in Scotland. So that's a good thing in some respects, because we know that the private rented accommodation people don't generally insure. But the situation in Scotland, again with your private rented sector, is not very good, really. This particular statistic, Scotland has the highest amount of tenants in conflict with their landlords for poor quality housing. A quarter of renters in Scotland say they have a slum landlord. Not only do they have poor housing, they're also relatively uninsured against flooding and other perils. So, just a reminder here, the tenure breakdown has a huge effect on flood insurance propensity. That's not because Scotland is less affluent than the rest of the UK. Figure here from Earnings in Scotland survey show actually that the annual full-time pay in 2015 was very slightly higher in Scotland than the rest of the UK, for which you deserve my congratulations. But when it comes to tenure and the affluence of the tenants, then you see that the poorest 10% tend to live in housing association and private rented accommodation, whereas the richest 10%, as you might expect, are owner-occupied. And that's a factor causing the level of underinsurance. The central belt of Scotland, where I showed you those maps previously of economic pain or annual average damage, actually, as you know, is one of the more affluent parts of Scotland. So it's not just affluence or poverty that's causing underinsurance. It must be something else. You probably know better than I do. Another worrying trend is that the private rented and the rented sector generally is increasing over time. And as we know from other reports, the amount of owner occupation is falling slowly. So this problem is probably growing in that those poor people in private rented accommodation are likely not to be insured properly against flooding. And the same is true about the rest of the UK. The private rented sector is increasing quite rapidly when you look at it in historical terms. So coming back to this rather dismal diagram, a fifth to a quarter of our population is inadequately insured against flooding and will suffer accordingly. And those are the people who are unlikely to have the savings. They're unlikely to have the resources which will help them recover from the flood that damages their property when it comes. Another reminder. So let me pass on to who gains and who loses, and this is not just about Scotland. If you look at the situation with regard to risk and insurance, you'll find that the variation in insurance premium is almost unrelated to risk. Two rather old PhD theses which I don't think have been confounded yet. Today, I think there's very little, if any, evidence that insurance premiums come down when there is investment in flood defences. Premiums don't come down, they stay the same. When SEPA or the Environment Agency invest heavily to reduce risk. So let's look at the logic of that. Individual flood victims who are insured do not gain financially from insurance when they're flooded. They should end up the same after the flood as they were before the flood financially if they're insured. But if there is investment, number two, from the state or others in flood risk management, event losses should decline. That's what the investment's for. If there's no such decline, that investment will not have been worthwhile. If there is decline in flood losses as a result of investment, then insured claims should be fewer or lower or both. This should be reflected, therefore, in lower premiums to be paid by those whose flooding has been reduced. If there is no such change in premiums, then the insurance company will retain the full premium income but have much lower costs. This should result in the insurance company making larger profits and giving larger dividends to their shareholders. So the logic of this, on this basis, all the SEPA and Environment Agency investment in flood risk management measures to reduce risk goes straight into the pockets of the insurance company shareholders because they don't reduce the premiums. Interesting, isn't it? Premiums are not particularly high. This is the average premium for a household policy in this country, coming down slightly, but it's still not an insignificant household expenditure. But we heard a little about Flood Re. Now, Flood Re is galloping to the rescue of people who are in high flood risk areas. It's an insurance arrangement for insurers. It's a reinsurance arrangement, which caps premiums at a certain level. But it's only available for those who insure, not available to those people who I've described as not insuring. What happens, and what will happen, what happens now, is that those premiums are set in future by your level of council tax bands. And the 5 bands here, with the A to H bands here. Flood Re charges the insurance these amounts, whatever the claims are that comes in. And that's a subsidy to those who would otherwise suffer by having large claims which cannot be met because their insurance policy doesn't cover them. A subsidy. But of course, the subsidy discourages self-help. You're not likely to do much to help yourself if you know that your flood claims are going to be heavily subsidised within the Flood Re arrangement, a major criticism of Flood Re. It also includes the very highest council tax bands in the country. So this particular estate in East Lothian, which I have a nice picture of here next to its river, the new owners of this bought it for £8 million in 2015, will be comfortable in the knowledge that their flood insurance will be subsidised by everybody else who pays the insurance premiums. A rather strange situation, you might think. But Flood Re has a finite life of 25 years, and the first transition plan has been launched by Flood Re last year. And what they hope to have happen is outcome B. They hope to move towards a fully risk-reflective pricing arrangement for flood insurance, which will provide available and affordable flood insurance to high-risk households. The other outcomes, A, C, and D, are less satisfactory. But this means, as Flood Re passes out over 25 years, that the subsidy will decline quite markedly as we move towards flood reflective insurance premiums. And people's insurance premiums will go up quite substantially. They will already be higher because they're now market council tax related, but they will go up in the future. But Flood Re hopes that that will not be the case by reducing flood damage costs. How will they reduce flood damage costs? Well, that's to be debated. But they want to maintain affordable flood insurance, and that depends on driving down the costs of providing it. You can do this by reducing the extent of risk, the cost of claims, and they say you can achieve it by greater competition in the marketplace. But how are we good at reducing risk? Well, in England, the Environment Agency's huge programme of 2.3 billion investment to 2021 will only reduce risk by 5%. It's hardly scratching the surface. I don't know what the situation is in Scotland. We could debate that. 5 minutes. Okay. Climate change, possibly increasing by 20%. So we have to repair flood damage better. We have to dry out our properties better. We have to have less temporary accommodation and try and get our administration costs down. We've been studying at Middlesex University flood damage for nearly 40 years. And this diagram here shows the change in real flood damage between 1977 and 2016. And what it shows is that real flood damage for the average residential property has gone up from something like £5,000 to £21,000 over that period. Why? Because your houses and my house is full of new things which are highly damage prone. I mean, we're not so full of them 40 years ago. Damage potential is increasing, not decreasing. So Flood Re is really up against it in this respect. There have been many changes in the methodology, but basically those figures are quite interesting and quite revealing. Why? Because our GDP has grown in that period by something like 1.98 times. We're 1.98 times richer than we were in 1977. And that's why our flood damage potential has gone up by something like 2 times. So how do we actually provide flood insurance which is affordable when flood damage potential is going up is a complete mystery to me. And also Flood Re has attracted serious doubts. This is from Daniel Johns from the Climate Change Committee. They're very cagey about data. They've only had 53,000 policies on their books after 6 months, whereas they set the target of some 350,000. If they don't meet that target, it means that Flood Re is well overblown, and we're going to be charged too much of it through the insurance subsidy. There is commitment to work together between Flood Re, but Daniel says there's no sign of it so far. They are accountable to Parliament, so maybe we'll know in the end, but we don't know yet. What about the future of flood insurance itself, to be completely left field? We're seeing huge improvements in data about flood risk, about the potential for harm. Perhaps this will lead to a move to unbundle a policy, so you can click to have flood insurance as well as your theft insurance and your fire insurance. Unbundling it would provide people with choices, and choices are what people need and want. Should we allow people to insure long-term rather than annually, so as to have a longer-term perspective over their cover that they receive? I wonder if we can have a situation where you insure just in winter. Why not? People are going to have choices. They demand choices. Insure in real time when floods are forecast. You could have a situation where that occurs. We're not stuck in the past, or we shouldn't be stuck in the past. So some conclusions. Flood insurance is really important to underpin all other aspects of flood risk management and can be resilient. Our insurance arrangements are resilient when tested internationally. But penetration is far too low for certain groups, especially in Scotland. The insurance industry in this respect is failing in its social duty. There are ways of providing low-cost insurance to low-income families. They're hardly being discussed, let alone implemented. Flood Re discourages self-help and perpetuates undesirable inequalities of assistance across community groups. I think the picture looks a bit grim today. The future looks no better. Thank you very much.
Are you all depressed now? But isn't there a real message that we have these pockets of long-time social deprivation in Scotland, and this is just another factor piled in those areas, despite hundreds and hundreds of millions of pounds of government money we've spent on it in the last 40 to 50 years. That's a really significant message, I think, from there. Final slot today. I'd like to welcome Johan Fazy from Dundee University. Johan heads the Centre for Environmental Change and Human Resilience, a really nice connection there. And he's going to tell us about that essential part of flooding community engagement. Johan, over to you.
Thank you. It's a real pleasure to be here. This is the last one. Hang in there. You're almost there. Okay. So just a quick set of acknowledgements. I'm going to be talking about a range of things, but there's a huge number of people who've put a lot of effort into the kind of information that I'm talking about. And Esther, the first person, Esther Carmen, is actually in the audience here as well. So talk to Esther about some of the work we've been doing afterwards. So I'm going to talk about managing flood impacts community engagement. It's kind of the interesting question. This is the people side. We started to get into that already with the insurance. I'm going to talk more about that. I think people are fairly central to this whole problem, and actually we haven't had a lot of talk about people so much in so far today. So I'm really going to talk about that. Now, community engagement, though, is a kind of slightly challenging kind of topic because it depends on engaging for what, with who, and all those kind of things. So I'm going to spend quite a bit of time talking around the subject about some of the background to this as well before we move into some of the details about the work we've been doing in Scotland. I just really want to put this into context. We're talking about climate change here. Climate change changes everything, absolutely everything. Meeting the sort of Paris Agreement around trying to achieve a 1.5 degree world is going to require really significant social, economic and cultural changes. This is not just minor change we're talking about. Reducing carbon emissions by 80% is a phenomenal task and will not be easy to achieve. So if we meet the goal of 1.5, well, we're going to get significant change. If we don't meet it and the world temperatures rise, we're going to get significant change anyway. So whichever way we're looking at it, this is about change. And I think the other kind of key point in terms of the context that I want to point out is we've done quite a lot in terms of science about helping understand the problem and possibly even identifying solutions. Where we're not very good at is how do we put these solutions into practice? The know-how, the doing, is a real challenge. So holding that into context, what I'm going to talk about is a little bit about a range of different things, but I will draw quite heavily on a recent project that we've just completed. In fact, the reports are available today now on the website, and this is a project funded by the Joseph Rowntree Foundation in collaboration with a whole range of other collaborators, primarily with Dundee and the Scottish Borders Council, where we did some work. So I'll be drawing on that as we go along. The key messages, though, that I really want to get across today are when we're talking about engagement, you need to know what you're engaging for, you need to know who you're engaging with, you need to design for whatever it is that you're trying to do and whoever you're trying to work with. And really the other key point is, well, kind of fairly obvious, but this, engagement is a complex social process. It's not easy to do, and we have to account for that in the way in which we work. So, the first point really, engagement for what? Well, we've kind of heard already today about all sorts of different elements of flood risk management. Are we talking about engagement for better informed decisions or better informed action by the public? Are we talking about developing and managing kind of resilience groups that draw on the capacity and the ability of communities and others to engage in flooding? Is it about engagement to enact wider changes, for example, wider catchment management and farmers? We're hearing about that already. Or is it about engaging with policymakers and so on, about creating the enabling conditions for these wider changes to occur? So there's lots of different reasons and elements of why we might want to engage. But what's really critical, though, is our underlying assumptions that influence how we go about thinking about what we might be trying to achieve. And I'm going to talk through a couple of these kind of assumptions. The first assumption is, what do we think the origins of the cause of vulnerability actually is? Are we talking about the cause of vulnerability primarily from a hazard, so the strength, the speed, or the frequency? Or are we talking about the social, economic, and cultural conditions that affect vulnerability of the communities we're talking about. This is a little village called Runaga, and it's in the southeastern area of the Solomon Islands, where I've done quite a lot of work in the past. It's a very, very poor village. There's no roads, there's no electricity, there's really no financial markets. It's very difficult for people to make money. It's quite exposed. There's not much space for food gardens. They rely very heavily on their subsistence kind of resources from the sea and from the forests. It's a tough place to live. And what we find there is that there are lots of underlying conditions that affect the vulnerability of communities to things like cyclones or extreme weather events. Rainfall, geez, they have 6 meters of rain there a year, every year. Rainfall is a big thing, but it washes away food gardens, which are really critical for people. And what we found really in the work that we've done there, and this is a very simplified kind of story of the Solomon Islands kind of issues, and that there's a set of underlying conditions and dynamics that really create that vulnerability. So I'm going to give you a quick story. It's quick. Basically what we've got in villages like this, an increase in number of people. It's affecting the pressure on the ecological systems. There's not enough space for food gardens and so on. It's increasing stress in communities. They try and make money to address that problem. The way they make money is try and plant cash crops. The cash crops then displace their food gardens onto less fertile, steep-sided slopes, highly prone to landslides and so on, so that increases the pressure. As you get more money in, you kind of get a desire for more money because they want more material goods. It does some positive things, like it increases access to health and education. They can get to the local clinic easier and so on. But it also kind of tends to move towards individualistic attitude. So in the past, people would come and help somebody build a house. Now they would want money for it. So the social cohesion in these communities breaking down, their ability to come together to address problems is decreasing. That increases stress and so on. So there's this complex set of dynamics, and what that really means is that if we want to address these kind of problems, we often think about income generation in these communities as a way forward, finding ways of doing that. But that kind of drives the system. It drives the system of planting more cash crops and so on. It doesn't necessarily alleviate the problems. So there's these kind of underlying conditions of increasing stress. You can see the spiraling kind of pattern of change that's occurring in these places. And what we find is that the vulnerability from this comes from these underlying dynamics. So if you add climate change onto that, where it's harder to plant the crops and so on, or you get more extreme cyclones, it's this underlying change and pattern of conditions that really give rise to the vulnerability. These short-term shocks are kind of important. Of course they're important, but they're less important in the long run than these underlying kind of conditions of stress. So that's really critical. So when we're talking about engagement, are we talking about engagement for addressing these underlying causes, or are we talking about engagement for addressing the kind of immediate hazards? For most of these people, the odd cyclone is not in their picture of kind of problems. It's much more fundamental and deeper kind of than that. In terms of the work we've done in the Scottish borders, we worked in 3 communities, and I'll come to that later on. But one of the kind of key things, we've seen similar patterns of dynamics of things that are happening there as well. I'm not going to go into the details, it's a bit too complicated, the story, but essentially you can imagine all these kind of complicated relationships between the different things that affect who is disadvantaged by climate change in a more general sense. And what we find is that the longer term stresses that affect the ability of households to balance their budgets are as important, if not more important, than the shocks from the flooding in itself. So these kind of underlying conditions where it's very, very difficult to, if you haven't got much money and you're having to make decisions about whether you eat or you heat your home, eat or heat in those kind of conditions, some elderly people in those conditions in some of these communities, and it's really, that's what you're going to focus on. So when you get changes from climate change like increasing food prices, that's going to have a longer term, slower stress effect on those underlying conditions as well. And that will then create the kind of critical thresholds at the point in which a flooding comes in and has a further impact on you. It's kind of similar to the sort of story you're talking about. When we're talking about the sort of disadvantaged groups, there are these underlying stresses that are combining and pulling together. They can't afford then the insurance to cover that and so on. And those are probably more important often than the shock themselves as well. And the other thing that comes out of it is that community capacity is really important. One of the counterintuitive things that comes out of flooding is that when you get a flood, lots of people come together. They then learn a lot more about who is vulnerable in their community, and that kind of reduces the stress for those who are vulnerable in the long term as well. So there's kind of a set of counterintuitive things that are happening there. So working on community capacity, so engaging people in that space, is really, really important too. And I think just really finally, just to point out and draw that out a little bit further, is this question of, well, what is a disaster? So there's a recent work by a PhD student of ours, Jade Patterson, who did some work in Jamaica. It's just passed a PhD examination now, and she was working with communities in Kingston, lots of kind of effects from things like landslides and flooding and so on. And when she asked people, what are the kind of disasters that affect you? They said, it's the drug raids. They completely wipe us out. So when the police come into their homes, they basically take away people's livelihoods. That is their disaster. It's not flooding. Yes, the flooding comes every now and again, but these are the bigger disasters for them. So I think it's really important to widen up the perspective and start thinking in a much more holistic way about the people that we're talking about that are affected. It's much more than flooding. I think really then what we're talking about, if we go back in terms of what we're talking about, what are we trying to engage for? We're talking about the shocks, the flooding. These are changing over time with climate change. The stresses are changing. The socioeconomic technologies and so on that are in society are also changing. And change is changing. So in the Solomon Islands, they talked about, they recognized that when we're asking about what has changed, they say, change is changing. It's getting faster. It's getting faster. This is, I don't know if you know this, the Great Acceleration. If you're just about whatever kind of variable you look at globally in terms of what's happening, in the last 50-odd years, there's been a massive increase. Paper production, water use, world population, carbon dioxide, surface temperature. These are all exponential growth. We're entering this period of great acceleration. So all of this is happening. And one of the things we tend to think when we focus on with climate change, we tend to focus on, let's predict what the hazard will be doing in 50 years. Well, the social conditions are going to be completely different in 50 years as well, right? So we have to be thinking about this in a much more kind of integrated and holistic way. So what does this mean then? Engagement for what? When we start talking to communities, they're talking about these multiple benefits, multiple issues that they're dealing with. Emergency management tends to focus on the now, on the immediate, on the flood itself, and so they're mostly talking about efficiencies, how can we do that better and quicker. Flood risk management is somewhere in between, but often we're talking in this kind of space, we're not talking about really what communities are trying to deal with in this wider kind of perspective of what we're dealing with. So is it about engagement for this kind of thing, or is it about engagement for this? And that really matters. So that's really the point I'm making there. Now, the second assumption that often we forget is when we talk about engagement, there are lots of different ways of thinking about engagement, right? So one of the kind of traditional ways of engaging or thinking about it, particularly comes out of the international development and the development work, is about participation. How do we get a wider range of people involved in doing whatever it is we want to do? This is an example really from the 1960s and 70s. The whole notion of participation was a move away from the style of top-down development that was coming out in the 60s and 70s internationally. And really this is an example of that. The Green Revolution in the 1960s and 70s, they were having to import huge amounts of food. Basically, there wasn't food in there. So they set up a whole process of science and technology, bringing them into villages and enhanced efficiencies in agricultural productions and so on. So, okay, great, fantastic. And it worked fairly well. You know, no imports of grains in 1976 to 80. But at the same time, there was an increase in extreme poverty, and there was an increase in landlessness. Extreme poverty, 38 to 53%, 20 to 50%. So really the point there was that this top-down process of let's put these technologies in place was, yes, it was increasing the food, but what was happening is it was mostly increasing the capacity of those who already had capacity or resources. So the wealthier farmers got the technologies and built that, allowed them to buy land from the poor that couldn't afford to do that. So it really failed. It really failed to raise up the population, and it actually increased inequalities. So really participation then was this notion, well, we need to work more with those disadvantaged groups. We need to find out what they need, and we need to find different ways of operating. So our assumption then about participation, what is participation, how do we engage, is really, really critical. And the key point really is participation about achieving a particular end? Is it about achieving a better flood defense? Or is it about something about learning capacity empowerment to raise up the status of those who are most disadvantaged in communities in the first place? And that's really the key point. If you're thinking about participation because I want to build a better flood defence scheme, okay, fantastic, and it might make it more efficient. This notion of participation as a means to achieve something. I'm going to engage with community groups to achieve a better flood scheme. That's fine, but it's less likely to focus on this capacity building, the alternative approaches, the multi-solving kind of ideas. You're more likely to engage in drawing out more ideas from different people. It may result less in continued motivation for engagement because you're not asking people really genuinely for their opinions about how they want to do it. Or is participation as an end in itself? Is it a process of empowerment where you go in and say, okay, let's talk about flooding, but let's keep a wider perspective and open about what is possible in terms of natural flood management, or how we tie that in with economic challenges you're dealing with, or how we tie that in with addressing disadvantage issues and so on in communities. So it's how we think about that concept of engagement, what we're trying to achieve by it is really, really critical. So the key messages, as I've gone through, we've covered this, know what you're engaging for. Well, who are you engaging with? In the Scottish Borders Council, we identified some key groups that were likely to be most affected by climate change, particularly around flooding. So elderly people with existing health issues, people on low incomes, local businesses, tenants, essential infrastructure users, families with young children, those kind of groups. These are the ones, again, that are less likely to be able to afford insurance, for example. So, okay, you might want to work with those kind of groups. But often what we forget is if this is a wider part of process of learning, engagement, capacity building, opening up spaces for addressing inequalities, then it probably requires us to be part of that process too. We have to be equal participants in that process of learning and rethinking our assumptions about what might be important. And that's really critical. So how do you then develop engagement strategies that are going to bring in local council people to think about it, or other organisations that might be working in there, to be part of a co-learning and co-creation of the solutions to the challenges that people are facing? And that's really critical as well. So that's the engagement with who. What I'm going to start doing now is just going to briefly kind of go into an explanation of the Scottish Borders project that we worked in, give you a bit of a flavour of how we kind of went about designing some of that, and just talk you through that a little bit. I'm not going to be able to go into too much detail about it, but just give you a bit of a flavour of some of those sort of things that are going on.
You've got 5 minutes to do it.
Okay, that's great, thanks. So, Scottish Borders, right, we're going to run out of time, but it's okay, no worries. So in the Scottish Borders, we worked in 3 communities, all flood risk communities, and were affected by the storms in 2015. Peebles and Hoyk got flooded, Newcastleton, people were evacuated. The focus of the design really was this looking at climate change in a broader sense. We were using flooding to get in there. We were also looking at climate disadvantage as a lens into it. We put a lot of emphasis on flexibility and structure, and it was very much about building conversations and relationships. It was a social process that we were engaging with. So it's about convening spaces for that. Multiple outcomes we were looking for. I'm not going to go into these in too much detail. Tangible. Could we build a flood resilience group out of the work? Capacity building. Can we enhance relationships? Learning. How can we share perspectives and understanding around that? The engagement was really critical. It focused. Esther Carman was our project officer. She was embedded between the university team. She was actually embedded in the Scottish Borders Council, working with the council, and then we used a kind of multiple set of processes for engaging out with different people using various snowball effects and so on. The key thing is we use a structure, and it was a fairly empty structure initially, to have a set of convening spaces, workshops where we brought community together, looked at futures kind of oriented things and tried to think about developing kind of actions around that. Lots of work in between to kind of engage people and bring them into that. And then finally, there's a policy kind of level workshop that tried to look at how we could improve the policy kind of level scope of the challenges in there as well. So that was the kind of the process of engagement that we involved. Lots of more detail around that, obviously, and you can have a look at the reports as we come into that. But I think the kind of key outcomes of really points that I want to make is that community resilience is a really complex social process. So these kind of diagrams, these are the metaphor. We asked people for their metaphors of what they thought their engagement was in. And you come up with all these different kind of metaphors, subjective kind of experiences of people involved in it. So some were patient passengers kind of standing there watching, being part of the bus journey, watching it go around the houses as it kind of people were trying to make decisions about what to do, and then kind of observed that. This was another one about forming groups as a person who was feeling that they were kind of on their own, trying to kind of follow this map. Other people came along with different interests, but again, in the end, they started to follow the map together and started to move forward. Another one here, just down the bottom, all aboard, lots of people coming into a boat, initially paddling in different directions, and then going around in a bit of circles, and then coming together as they realized that other communities were dealing with the same sort of thing. So this kind of just realized that this is kind of a complex social process where people are going to experience this in very, very different ways, and not always positively either. So it's a complex social process involving negotiations of power and control. It can contribute to greater shared understanding of goals. It requires time to be developed and sustained. So there's a kind of whole set of things that are coming out there that sort of demonstrate this is not something easy to do, and it takes time to start building those relationships to then allow you that capacity to take things forward in the long term. Lots of kind of design elements that you might think about. I'm not going to go through them all, but really this one was really key. Facilitation and participation expertise. We always think about the expertise, the technical expertise we need for doing a flood risk management or something like that. We hardly ever think about, we actually need expertise and people who are experts in gathering people together and working through complex challenges, working with different values, working with different perspectives. That's really difficult. It's not easy, and it requires a lot of time and effort. We put tons of time into doing kind of assessments of various vulnerability and so on. We often don't put the time into this, and that's really, really critical. And then finally, it's working with lots of tensions. Here's a whole list of tensions. You know, is it about trying to achieve a degree of holism, a wider perspective, or achieving a particular specific outcome? Is it about quick wins versus a long-term change? Is it about participation, lots of people involved in that process, seeing that as part of the process, or having a very specific direction? Is it about data collection versus action? Is it about independence from outsiders or being embedded inside? There's a whole kind of set of different tensions in there, and that has to be managed, what we call a dilemma dance. It's kind of, you've got these two extremes. You put holism at this end and focus at this end. Somehow you've got to find a middle ground, because there will never be something that's completely obvious about what you might be doing. So it's always going to have tensions, and all of this needs to be kind of carefully managed and integrated and so on in various different ways. It's not easy. It's not easy. Anybody who's trying to change anybody to do anything, my wife, just getting her to make sure that the windows are closed when we put the heating on, it's a nightmare, right? So imagine that. That's tiny compared to all this sort of stuff. So let's not forget that it's complex. So conclusions. I think we really need to be starting with people. That's what we're talking about. Systems, approaches, we're starting to see that come out with these multi-solution kind of ideas, but we need to engage with futures. We need to engage with creativity, imagination. We need to bring in the different expertise that's available in the room in various different guises. Farmers are experts of their own farming. Local people are experts of their own lives. These are really, really critical. We need to flatten that base and start working in that way. Engagement is a complex, messy social process, and we need this expertise. The reality is, though, that this is really difficult. There's not a lot of resources. Shouting for more resources is not really going to help. We've got to find some different ways of working in this. I don't have the solutions. However, the potential opportunities arise from exactly what I'm saying, which is partnership working, seeing things in a wider picture, making those relationships work. It's also about holistic and integrated solutions. You find the solution by taking the wider, bigger picture. And we're seeing that already from some of the things that have been talked about. If you open that space, those solutions will come. And then finally, I think it's about more integrated policy landscapes and for things like capacity building. We're not doing that very well. We're not linking the Community Empowerment Act with the Flood Management Act, for example, or the Climate Change Act. We need to start thinking about these things in integrated ways, and we need to be doing much more of that. Thank you very much.
Thank you very much indeed. That gives us a different perspective, bringing in not so much, let's invite the community in, let's actually think about how communities react. Is this working? Yeah. Okay, questions please for any one or all of the speakers. Yes, Tom. In the middle here. Fourth row back.
Yeah, question perhaps primarily for Edmund. Tom Letherland. You mentioned the idea of when flood risk or flood prevention measures are put in, then insurance premiums go down for that small area. But we also saw that the proportion of area, potentially flood-prone areas where measures are getting put in is actually a small proportion of the total. And at the same time, I have a suspicion that if climate change is happening, which I believe it is, then the likelihood of flooding occurring somewhere must be actually increasing. And I would have thought that percentage increase was probably as much as the small decrease that you're getting where you have put in a flood prevention measure.
All right, I understand the question. You're saying that the change in risk outweighs the investment expenditure in that locality. Well, that may be the case, but it's poor. It's a poor message to give the people who have invested in that particular scheme to see their insurance premiums not fall. And in the meantime, before your increased risk occurs, the money still goes into the shareholders' pockets because the costs of insurance are less, but the income is the same. I'm repentant about that.
Okay, lady at the back, please.
This is a question for Michael. I'm just wondering, in some communities, they have some active community groups that kind of help broker the messages from the flood warning and really help galvanise action in the community. Did you look at the role of any community support groups in kind of translating and brokering sort of information and action?
That was one of the questions we asked in the questionnaire. Are you part of a flood group? I don't have the response in terms of did that mean there was a more effective response, but that will be something we're looking at. So good question. Thank you.
Then the gentleman 2 rows down. Thank you.
Hi, Connor Price. I'd like to query Edmund in relation to his understanding of the insurance industry and what level of flood risk they would consider to be acceptable. So, for example, I would assume that the 1 in 10 year flood event would be of concern to them. I understand that the 1 in 75 is often considered the threshold, but is the flood industry or the insurance industry concerned about the 1 in 200 or the 1 in 500 year level of flood? And from the perspective of a flood protection scheme, is there a level that we should be targeting when you consider the opposite side of that equation?
I think the insurance industry, well, the industry as a whole is concerned about major events because those are the events that could lead it to be insolvent. And therefore, the government requires the insurance industry to be able to meet the costs of a 1 in 200 year event. That's the regulator's approach to it. Whether they are concerned more about the 10-year flood than the 50-year flood, I don't know, actually. Because you have 5 times more 10-year floods than the 50-year floods. So I'm not sure that it doesn't even out in some sort of way. I haven't heard of any differentiation between different return periods and industry concern. Only about that top one of 200, where they must meet the regulators to have sufficient financial resources in the bank, if you were, to be able to meet the 200-year event.
Are we getting tired? No, you've had a shot. And James is gone, so he doesn't get another shot.
What question would James have asked?
How do you pay the farmers for being stewards? Anyway, but I'm not getting into that area. Yeah, and I'd like to ask you, this very crucial area of engaging with or getting the communities on board. One of the things I find when, a bunch of old men who are my neighbours, which includes me, think, the river's going to flood because there's high water and there's a storm surge, and they all know the answer. I've got a totally different answer for them, of course, because I'm a geographer, but how do you deal with these really set views in these debates when you've got that sort of polarity? And they're saying, well, what do you know about it anyway? You're just an academic from the unreal world.
I think that's a really good question in which there's no easy answers. But the way I've approached it is that you try and create spaces where it's a co-learning. And that's the only thing you can do. And the only way to do that is to go into that space on the assumption that you need to be one of those learners as well. And really that's the only way to do it. And there are lots of different ways of creating those spaces, and but it does really come back to, as I said, having that expertise in participation and facilitation, which is really, really critical, and having people who really understand the processes that are involved in that. And one of the key requirements of those kind of people is that they have to be independent of that process. So it's kind of seeing yourself as, the project that we ran in the Scottish Borders, I did quite a bit of the facilitation participation, but that was challenging because I wasn't really independent. I still had, a report to write out of it and things like that, so you're dependent on certain outcomes, and that can be challenging as well. And it requires time, and it requires patience, and it requires different kinds of ways of approaching it. I mean, one of the things that, as I said, the flooding did impact on the communities while we were working there, and that completely changed the extent to which people obviously engaged in our project, not surprisingly. In Hawick, we had a workshop that was already set up. It turned out to be 5 days, I think 6, 7, 8 days after the flooding, which was phenomenal. So suddenly we had a pile of people coming into a space that had really, really strong perspectives and views. But we used a particular method which helped us give them time to talk about the challenges that were dealing with. Flood insurance was coming up a lot. We had a method then that allowed us to then separate that from their wider aspirations of what they wanted to achieve from the town. And the interesting thing, when you start talking about the present, they're talking about flooding. When they talk about the future, they're talking about urban regeneration in Hawick. So there's a real difference. And so what we then were able to use is that space to talk about how, there's a design of a flood scheme coming in, how can we change that design to help achieve the future they wanted, not just to address the flooding. So you can find commonality once you've agreed on the problem, and that is often the way forward. Yeah.
Yes, Chris.
Thanks, Chris Spray. It's perhaps a sort of comment on what Johan's just said. If I go back a few years when I was wearing a SEPA head and look at a different part of Scottish Borders Council, and different part of that area, rather, we had a major problem with flood issues, and between ourselves as SEPA and the Borders Council, the only body that actually could go in was a total independent trusted intermediary, which in this case is Tweed Forum. They were able to go places to have conversations that even if we had all the structural skills we might have learnt in academia, there's not a chance in hell we could have had it, because we came with all the baggage. They actually could walk away and walk in without having to achieve a result, in a sense. It's a very different one. So that was a scenario that, let's say, came out of a fairly dramatic event. It's probably about 15 years ago, so I've almost recovered from it.
Yeah, I think, Chris, just briefly, I think that's true. I think what we were trying to do in the Borders project is actually create the spaces where you develop those relationships, so you didn't have to be in that situation in the future. And that's where you need the longevity, because you start building those partnerships, those relationships on a basis of trust. It's much, much easier to then continue that. The challenge of our project, it was 18 months, so we'd really only just got started by the time the project ended. And that's one of the challenges. How do you continue to do that kind of work when councils don't have the resources to work in 3 communities? They've got to work in 60 communities. And they just don't have the staff to do that.
Yeah. Gary.
Question for Michael. You set out a very sort of clear explanation on the improvements of flood warning that had taken place in Scotland over the past decade or so. But if we pick up on Edmund's point that we're moving to a world where people have more choices, and one of the choices might be sort of real-time flood insurance, where you click a button and say, I want insurance for next week. I mean, how far are we away from getting that quality of prediction into our flood warning systems?
Good question. I think it depends. Obviously, a number of the flood warning capabilities and forecasting capabilities are quite advanced now. I think I've presented the case in the last 10 years. It's not the case with surface water forecasting. Clearly, there is still a lot of uncertainty around that, so there's still a lot more challenges to go before you would be able to put that action in place based on alert. So, yeah, depends.
It's interesting. Warnings are really problematic. I like the quotation from your Scottish policeman. I mean, I've talked to people about the 2007 flood in England, and they say, we were never warned. We were never warned. And yet the television every night was going bang, 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 all the time. Oh, yeah, but nobody knocked on our door. So the warning that they wanted was personal, not just the television. And that's the problem that your policeman had.
Yeah, I mean, that's clear from a lot of the evidence that's come back through the research is warnings need to be more local, more relevant, more applicable to the individual. Now, clearly that could be possible in a lot of cases where there's a lot of data and information and forecasts to provide that to the communities. Where there isn't, you've got that gap. And particularly with the flood alerts, things like that, they are too broad, they're not relevant enough for the people that receive them, and that's all they get.
But can I follow that up? You know, we've all got mobile phones, we get these warnings. But there are groups in our society, I mean, you flag those up, the elderly particularly, who don't have that facility. Mm-hmm. You know, how do we make sure that they're not made even more vulnerable in these situations because they don't have access to this?
Yeah, yeah.
And there's no telephone directory of mobile phone numbers like there is on landline numbers. If you want to find the landline number, if somebody who lives in number Smith Street, you can find it. You can't find the mobile number.
I think when you mention the more elderly, when we look at the demographics of the people who've responded, it's actually at the higher end of the age categories that have responded in terms of the flood warning service. Those between 18 and 30, less inclined to engage with the floodline service, flood warning service. They're more difficult to engage with in terms of signing up and taking action.
Last question. Just a question, please, not a speech.
I'll be brief, promise. Miguel Piedra from Arop.
Sorry, I thought it was that guy. Yeah, sorry, I still I didn't mean that comment to you, sir.
I forgive you. A question for Mike and for Ian. It's more a thought, but I will phrase it as a question to try and prompt discussion. To what extent improving community resilience, community engagement, the second type of community build-up you explained, and also the advancement in flood warning will reduce the need for real hard defenses and investment on defenses, which we seem to run out of money on not being able to keep up with.
Hmm. Well, obviously you can see from the figures that clearly people are taking action in terms of property level resilience measures. People are responding to the warnings. So that message getting out there. I think there was a Scottish Government survey or research a couple of years ago about how effective they could be on a community scale. So it's worth referring to that piece of research in terms of the benefits wider across a community rather than at an individual level. So yes, I think there are potential benefits there. It does lead to requirement for effective flood warning. An engagement on a local level and make sure it's locally specific to them. If you want to.
Yeah, I mean, there's no easy answer to that. But I think there are. It's obviously part of the solution, but you have to be thinking about solutions in a much wider perspective. There will always need support, but there are also some really significant capacities I don't think have been tapped into yet, and it kind of you have to start thinking about a shift in who has ownership of the problem and who has responsibility for the problem as well. So there is potential, but it's how that's enacted I think that's really critical, and the way to enact it is to see it in a wider picture.
Final question. Just a question. No, you can't because of the recording system.
Thank you. And sorry, I'm in the habit of giving speeches, but I won't do it this time. The question about how do you engage with old people, infirm people in the community. In the Edinburgh floods some years ago, which I was involved in, we introduced the concept of neighbourhood flood watch. Not neighbourhood watch, but neighbourhood flood watch. And the neighbourhood flood watch scheme worked because neighbours knew who the vulnerable were, they listened to the radio and so on, and they engaged with their community to try and prevent it. And I'd just like to say, it is a speech actually, I'd just like to say the social dimension of flooding is the most important dimension of flooding. And that is what we really have to work on. I'm not being negative about the amount of research we do into climate change, etc., but we should spend a bit of time in the social dimension. Thank you.
Thank you very much. Well, I'd like you all to thank our three speakers who have done us proud for the last speaking session of this meeting. Thank you all. Thank you. Now, don't you close the doors now, because Gary Pender and I are going to tell you what today's all been about. Let's see if you've been at the same meeting as he and I have. And Gary's going to kick off, I think.
I'll kick off, yeah. So thank you, Roger. I mean, I've had an absolutely fantastic day. I think everybody else, or I hope everybody else has as well. The speakers have done us proud. One of the things that's really struck me is the sort of coherence and the seamless movement from one talk to the other. You would almost think it had been planned by the organising committee. It has been a long day, so I'll try not to take too long, but I do feel I should give a sort of summary of the kind of scientific aspects of what we've heard about today. We started off with Chris Kilsby, who spoke to us about the challenge of finding trends in extreme events, whether stationarity was dead or in fact undead, and the fact that even surprise events were sort of unsurprising. So light-hearted touch, but certainly some very important scientific insights into the statistics of flood extremes. We then moved on to Nick Reynard, who also gave a very interesting talk on the work that CEH have been doing on global climate modelling, downscaling that to a catchment scale, using the catchment characteristics to sort of rebuild things up, to discover that different catchments across the UK had different characteristics and would respond differently to climate change, and then coming at it from a very practical perspective and investigating whether the 20% additionality that we have been using for climate change was appropriate, and reaching the conclusion that for different catchments we needed different percentages of additionality, and that would be somewhere between 20 and 40%, depending on the catchment characteristics. So really practical outcome from some very detailed research and detailed and difficult computer simulation. Next we had Hayley Fowler, who spoke to us about the challenges of simulating convection storms and how you had to use really refined grids to capture the physical processes that were taking place within these cells that are, you know, relatively small scale to some of the things we think about in terms of flooding, but can have significant impacts and cause significant floods because the rainfall's intensities associated with them are really quite high. So again, really high quality, difficult science that's having a real impact in what we do as far as flood management is concerned. Then we moved on to Mark McLaughlin from SEPA, who updated us in SEPA's flood mapping and how these maps could be used. Very practical, honest approach from Mark on the use of maps with and without flood defences included in them, what SEPA could do to enhance their flood mapping in future, and that sort of approach they had to continually upgrading the quality of data that we in Scotland have available to us. I was particularly interested to hear about I think it was FedCap, the app to collect real-time data during floods. I think that's a really fantastic initiative to use up-to-date technology to feed in to improve flood modelling. As a flood modeller myself, data is the absolute key to trying to improve these things. So, very, very important. After lunch, we started with David Bamforth. David, being an engineer, very down-to-earth approach. He told us that water flows downhill, and when it stops, it forms puddles. I didn't know that, actually. That's something new I learned today, but that's fantastic. But joking aside, excellent summary of sustainable urban drainage techniques that we can use in the urban environment, ranging from multiple uses of infrastructure during flooding, insights into what they're doing in the Netherlands with no subsurface drainage in some of the estates, adverse cambers, and trying to control the water on the surface. And then the example about river realignment, combining both water management with amenity value and social enhancement. So I thought these were all excellent examples that we can learn from and implement. Then we had the sort of mirror image of that presentation from Mark Wilkinson on natural flood management here in Scotland, and the work that the James Hutton Institute have been doing on retention ponds, buffer strips. Mark actually also mentioned sediment and erosion and the problems we can have with sediment in some of these systems. I particularly thought the example on the James Hutton, is it a research farm or something that you own up there, but the idea that you break the land drains, you allow the water to flow through a bioactive root zone into buffer strips at the edge of the field, and not only does it have benefits to flooding, but it also helps you manage it. The nitrate runoff from the farmland was particularly interesting and another good example. We then had Mike. I knew that was a difficult question, Mike, actually. I just thought I'd test you out there at the end, but Mike gave us a very succinct update of how far we've moved forward in flood forecasting here in Scotland over the past few years or so, and it was really interesting to hear about that, the percentages and overall satisfaction, the way in which people's behaviour has changed as a consequence of these enhanced warnings was all interesting to hear about, and how the key to this is actually trying to motivate people to take the right decisions in light of uncertainty associated with climate and with rainfall was also a useful learning point. Edmund, as always, gave us a fantastic insight into the insurance industry, the role of the insurance industry in flood risk management, how the overall robustness of the industry is important to us, the pain threshold, which was a new term to me, but it makes absolute sense when you hear about it, how areas of deprivation here in Scotland mean there's higher pain thresholds in these particular areas, and then an insight into what the future of floodary might be, and how we might have to think about how that's going to transition in the future was also useful to hear about. It was also good to hear that people in Scotland actually have a higher annual income than people elsewhere in the UK, although he stopped short of making any comments on why that might be politically, which I think is probably quite a sensible thing to do when you're speaking in Scotland, Edmund. And finally, Ewan talked to us about the complex social processes associated with taking some of these decisions in flood risk management, and how you motivate people, and how you need to think about social interaction actually as a system rather than a sort of thing, and the whole difficulty around discussing these things with people, how they need to be able to run meetings appropriately and not just think about the technical aspects, was absolutely critical, and he left us with the thought about if we want this to be successful, we've got to think about learning capacity and how we actually empower people, which I thought was a really good message to hold in our minds as we moved on. So these were the key points I took from today's meeting. As I said, I've had a fantastic time. I've really enjoyed every presentation. I hope you have too. And I'll pass back to you, Roger.
Yeah, very good. Well, I've learnt a lot as well, which is really good. People of my age always think we know all the answers, and it's what really pleased me today is not just listening to the speakers, but to see the age structure of the audience. It's so good to have so many young people here. And when I look at the list, I see that you're in engineering companies, you're in statutory agencies like SEPA and SNH, and in local authorities, as well as the universities. And that's just the audience that we're looking to capture with these events in the RSE with our various partners. I was struck this morning, somebody said too much focus on scientific assessment and not enough on practical solutions. I mean, it strikes me with a foot in both camps, if you like, that it's very important that we have the scientific underpinning, recognizing all its uncertainties. Scientists are really good at telling us what the uncertainties are, but there are some head points that come out. But there are some known knowns in these things, not just that water flows downhill as well. And how far can we use and translate that evidence that we are gathering all the time through these amazing multidisciplinary studies in many universities in Britain, translate that evidence into the practical flood risk reduction and management. If I had my headlines for the public, thinking forward to our next session and thinking forward to what we want to put in our advice paper, which will go to all the MSPs and everybody else who wants to listen and we hope might listen. First is the scientific bit. Flooding's been with us for generations, and I think that's a really powerful message. We tend to think that we've had more events, and I think it was a salutary lesson in analysis of data over long time series this morning. And the present trends are actually consistent with that much longer time series. But at the same time, there are clearly predictions of more extreme precipitation events. And with that, extremes are a lot of uncertainties attached to it. So there's no simple answer. What I think has come out beautifully today in all of the case studies that have been presented is how we deal with the spatial variation of the data and the putting in of management solutions. And it's something we sometimes forget in Scotland. Scotland is not a level playing field in addressing these matters, and it's okay to have an Act of Parliament and a statement from whatever government's in place and its agencies, but unless we recognise that spatial variability in the phenomenon, but also in the people who live in those areas with all of their diversity of socioeconomic circumstances, we're not going to get anywhere. The next point is that if we're going to live with flooding, and this is a very dangerous statement to make, because of the uncertainty of connecting the flood point with climate change in any convincing way, and given all of the people on the right wing of this argument, of which, and I'll be perfectly blunt, there are rather a lot of them and are very vocal, getting over the message to the public that this is all to do with climate change as opposed to lousy upland management, poor planning in urban areas. I leave that with you to reflect. You can hammer me afterwards if you like, but let's try and think how we get these messages over. Next, well, it's pretty important that everybody gets insurance. I think the clear message there is that, well, Flood Ray is perhaps not working because it's not hitting those elements of the population which are already intensely deprived on every other socioeconomic indicator. And that's, I think, a very important one for our society to make that clear to government when it's looking at these issues. Next, well, it's identifying where the problems are. And I think it's really superb, the work that SEPA has been leading on with a whole lot of experts of looking at the spatially specific data collection and its use on flood risk. David knows that I've been very critical of the old SEPA maps. I looked at them before I bought my house and rang up the insurance brokers. Now we've got a much more sophisticated data collection system for inland and at the coast. And I think that's vitally important that we, the public, support the continuation of that work and make sure that the government doesn't pull the plug on it in times of austerity. And we have now got the development of excellent flood warning systems. Let's make sure that all of the people we would like to sign up for those warning systems and that we make them as available and as amenable to the customers as possible. It's really good this survey has been done. I congratulate you on that. And finally, we have to keep demanding the connected solutions to these sorts of issues. I still find, as a former civil servant, that there is a government which is very good at operating in silos. And we need to make sure that we've got the connected solutions, because we know from what we've heard today is that the connected solutions are not just about flooding and flood risk management. They're about giving a whole lot of other multiple benefits, which people on the ground really appreciate. And we've got wonderful examples we've heard today, natural flood management and what I'd like to call nature-inspired engineering solutions as well, in rural areas and in urban areas, on intensively managed land and on land which is, let's face it, probably overbuilt on and over-engineered in terms of overland flows. And finally, this importance of meaningful engagement of all the stakeholders, the people that can cause the problems, like the planners. I don't think I've heard the word planners mentioned today, and building control people. They are very significant in this, as are the farmers and the wrong signals from the Common Agricultural Policy, which hasn't been heard much about today, but that's very, very important indeed. Obviously the affected households, wherever they are. So I hope you've all taken some really good material back to wherever you're working, back into society. Thank you all for coming. I'd particularly like to thank our sponsors. If I had the piece of paper, I'd be able to read them out. Yeah, Gary's got it here. John Hutton Institute, Scottish Government, Scottish Natural Heritage and SEPA coming together, which is extremely important to get that strength of support. I'm really grateful to all of my fellow chairs, to the organising committee. We worked on this for many months, and I hope you, as the audience, recognise how valuable this is to you. Thank you all so much for coming, but we haven't finished yet, because not only have we got a public engagement session later on, we will be producing an advice paper with our speakers, and then we're also hoping to publish the papers, if the speakers produce them in a reasonable time, hint, hint, in the Scottish Geographical Journal, which is available to the 2,000 members of that society for free and to any others. So we've not finished, because these meetings are all about getting messages out to wider community. And before I finish, I'd like on all your behalves, all of our behalves, to thank the guy who's led all of this, Alan Werrity, for driving it forward. So thank you all very much. Now the practicalities are there is a